just going to give it another minute while people trickle in. I think we're looking good. Hello, everyone. Welcome to the Types 2 session. As with every session at this POPL, we're aiming for about 17 minutes for talks and 3 minutes for questions for a 20-minute total time. We're going to start off with Orpheus presenting affect, or effect, an affine type and effect system.
Yes, hello. Yes, my name is Orpheus Van Rooij, and today I'll be presenting you indeed an affine type and effect system, which we call affect. And this work has been done in collaboration with Robert Quibers. So the problem we are facing is that when we have a language with ML-style references and we have also multi-shot effects, these two features can cause problems when put together. And this is particularly a problem in languages such as OCaml. And our solution is to introduce affine types to an effect system in a way that distinguishes between effects that are one-shot and multi-shot. And to make the system more expressive, we incorporate ideas from Rust cell type and Wandler's use types. And we have formalized the language as a proof of concept, which we call the language we call as affect in Iris and Rock. And we have proven, mechanically proven type safety for it. So before I go deeper into the problem, let me give you a quick introduction into effects and handlers. So firstly, effects need to come from somewhere, and they come from the so-called operations, which you can think of them as just some syntactic entities. So for instance, here choose takes a unit and returns a Boolean. And we can use choose to define this effective function uno, which allocates a reference r with the value true, simply performs the effects choose, and the response from the effect, it puts it back to the reference, and then it just reads back what we just stored on the reference. And here, if you can notice that on the function type, we also annotate the effect that the function produces. And this is because choose is really, as I mentioned, is a syntactic entity. It has no intrinsic semantics to it. And to give semantics to choose, we have to install a handler for it. So let's do that. For instance, we can choose to always respond to false whenever we get a call to choose. And to do this, we install a so-called effect handler, which you can think of that's some kind of like a generalization of an exception handler, where it also takes an extra argument, an extra continuation, which you can see this K, this continuation, which gives you a way to respond back for the handler to communicate with the effectful program that it handles. For instance, when we apply choose false to uno, the example from before, the continuation K really represents what the part of the expression that comes after the effect call. So really what you see here, the part of the expression that's surrounded by this dashed lines. And the argument that we apply K to, K false, is put in this whole of this continuation. It replaces the to choose operation. So really it gives the ability for the handler to communicate back to the expression. I also want to note here that choose false is a one-shot handler because it calls its continuations at most once, exactly once in this case. Alternatively, we can collect all the possible evaluations of the effective program. Where to do this, we install a different kind of handler where we call the continuation with both Boolean values and we collect all the possible results in a list. And I'm not going to go into details how exactly this handler works. But the main intuition here is when we call collect all with uno, we will get a list of false and true. Because all that uno does is really just calls the effect, stores it back to the reference, and then just loads it back. And here, collect all is what we call a multi-shot handler, because it calls its continuation more than once, exactly two in this case. So now that we are experts in effects in handlers, let me go a bit deeper into what the problem is. And we outlined two problems. The first problem is concerning the implementations. And the problem with multi-shot effects, specifically when we have the continuations of multi-shot effects, is that whenever we call them, we have to copy again the whole continuation closure of it, because it might be still callable in the future, so we have to somehow need to keep track still the structure. So essentially, multi-shot continuations are quite inefficient to implement. And also, the second problem is regarding optimizations. The problem here is when we have expressions that perform, that use references and also perform multi-shot effects. Now, many common compiler optimizations that you can do on such kind of expressions are not sound. And this is particularly a problem in languages like OCaml. And their solution for that is basically to forbid multi-shot effects altogether by throwing a runtime error. But we think that this is not a satisfying solution, firstly because they don't statically track it, that multi-shot effects are being used, and also that multi-shot effects are quite useful also. So let me give you an example, first of all, of an unsound optimization. So for instance, consider this extension of Uno and call it Duo. And all that Duo does is basically, instead of just calling the choose effect and then store it directly back in the reference, as Uno does, we call the response of the effect, we apply it with the logical AND operation with the value of the reference. And notice that we can apply some simple optimizations to this. So for instance, we can propagate the initialization value of the reference, true. And then we can eliminate the logical AND operation true, because it really doesn't do much. So essentially, what we have done is we have optimized Duo into Uno. And in the one-shot case, so if choose is only handled by a one-shot handler, this is perfectly fine optimization, it's sound. But in the multi-shot case, it's actually unsound. And for instance, if we call collect all, the multi-shot handler from before, we call it with collect all Duo, we actually get evaluated to a list of false false. Whereas if you recall, when we called collect all Uno, we got a list of false true. So the semantics are not preserved, essentially. And the reason for this is that because of references, because we also have references in the mix, a call to continuation is somehow it's aware, it can know whether it has been called in the past, much like in what happens in the Groundhog film, if you know the film. But the point here is that when, for instance, in the example of the collect all handler, the first call of the continuation with k faults, what happens is we apply the logical AND operation with true. And this is, at this point, optimization is fine. So we are all good. But on the second, when we do the second call to the continuation with k true, what is supposed to happen in the Duo is apply the logical AND operation with false. So here is where this optimization really is unsound, it breaks. So the point here is that with multi-shot effects, this optimization is not sound. And we want somehow the compiler to stop it from applying such kind of optimization. And our solution is simply to give more information to the compiler. Specifically, we develop an affine type and effect system, a way that distinguishes between effects that are one-shot or multi-shot. So for instance, choose can either be given a one-shot effect signature, which we denote using this double lolly. So if we give it a one-shot signature, means it can only be handled by one-shot handlers. Or we can give it a multi-shot signature using this double arrow. And by distinguishing between one-shot and multi-shot effects, we are able to address the two problems that I've just mentioned. First of all, regarding copying, that if we have one-shot effects, the continuations of one-shot effects, they don't need to be, they can just apply a destructive resumption on them, because we know that they're not going to be called in the future, so we avoid expensive copies. So we get some kind of benefits from tracking this information. And regarding the optimization, now the compiler has more effect type, knows more information about what kind of effects the expression performs. They're called one-shot or multi-shot effects. And so it can know what kind of optimizations to apply. So, and the language that we consider for this system is the language with effect handlers, with ML-style references and affineness. And this combination of features hasn't been studied before in the context of substructural effect systems. And I'll now show you that this combination brings some challenges. So what are these challenges? The first two challenges are regarding the expressivity of the system. The first problem is that it is a common pattern for many effect libraries that also make use of references to actually store one-shot continuation or continuations into the references, which is a little bit of a problem because references are used to share data, but at the same time also want to store affine data in them. So how can we do this in a sound way? Second problem is regarding polymorphism. If we have some usual form polymorphism over types and effects, an unbounded form polymorphism, this is actually unsound in such a system, that we consider, because of the way affine data interact with multi-shot effects. So how can we still have some kind of polymorphic types in the system while still being sound? And lastly, how can we ensure that all these features of the language interact nicely together? So specifically, how can we prove type safety, but not just regular type safety, but also that the usage guarantees, for instance, of one-shot continuations are obeyed? And our contributions address these problems exactly. We're inspired by Rust cell type, and we have our references are shareable regardless of if they store affine data or not. We employ a form of bounded polymorphism by extending Walter's use type to effects. We take a semantic type soundness approach to prove type safety that also incorporates the one-shot guarantees. And lastly, we have normalized the whole language. In Iris, we have mechanically proven type safety, and we call this language we call affect. So let me go a bit into the more zoom into the contributions. So first of all, we have our cell-like references. And the challenge here is that if we naively just combine references that are shareable, but at the same time also store affine data, well, it wouldn't be very sound because we can just get an affine value, store it behind the reference, share the reference, and we can get the value twice from every alias of the reference. So we need some kind of a restriction of the operations of the reference. And our solution is to use a cell-like inspired API. So the operation that we can do on the references, we can only load for the reference from a reference if the value that the reference stores is of an unrestricted type, in contrast to an affine type. And if you want to deal with affine data, we use this replace operation, which simply just acts like a store on a reference, but also returns the previous value of the reference. So the replace allows us to deal with affine data because the concept is very simple. Essentially, whenever we want to get the affine data back from a reference, we have to store something back. And the observation here is that many challenging examples from effect literature, such as a library for cooperative concurrency, that heavily relies on storing one-shot continuations into references, it can be easily adapted, and we have adapted it and have type checked it in effect, and by using this replace operation. So we can ensure that the one-shot guarantees are not broken. The second contribution is regarding polymorphism. I have said that we use a form of bounded polymorphism in the form of use types. But let me give you an idea of what the problem is here. So consider this small example called foo. It is just an abstraction that performs the effects choose and then returns its argument. And the question here is whether we can be polymorphic over the argument type while still give choose mark choose as a multi-shot effect. You can see here with the double arrow. And the answer is no. It's unsound because if we call foo with some affine function, which is the affine function is v in this case, then this affine function will be captured in the continuation of the effect. And this is a very bad thing. We really should forbid this. So capturing affine data in multi-shot continuations breaks all the soundness because we can easily get this affine function twice by just installing a multi-shot handler on the expression. So in actuality, there are only two sound possibilities to give to this effect. The one possibility is to allow any kind of argument type, but restrict choose to be a one-shot effect, which you can see here from this double lolly. Or we can be polymorphic only over unrestricted types, which we express using this bang type former on alpha, which is inspired by the bang type from linear logic. But then in that case, if we are polymorphic over unrestricted types, we can have choose as a multi-shot effect. So the challenge here is how can we express both of these two possibilities in one type signature? And to this end, we introduce a dual to the bang type former, which we call the flip bang effect former, and incorporate this into a Wadler's use type kind of form. So we introduce a novel effect former, which works on effects, and we quantify this bang, and in our case, the flip bang, over variables, just like what happens in the with the use types. So here, new ranges over once and multi, and for every instantiation of the two actually gives us one of these two possibilities. For more detail how this works, you can see the paper. Lastly, I want to say a few things about how we prove type safety. And specifically, what we want to show is not just regular type safety in some like no usual type errors, but we also want to show that our one-shot continuations are really called at most once. And it's this combination of wanting to guarantee that one-shot continuations are called at most once, and having these cell-like references where we share, our references are shareable regardless if they store affine data. This is what makes syntactic type soundness approaches it's less clear how they can be used, at least in this case. So instead, we take a semantic type soundness approach. And to do this, essentially what happens in a semantic typing setting is that we interpret our typing judgments, our effects, our types into some kind of semantic domain, which in our case is the separation logic of iris. So we build a logical relation in iris. And the main idea is that you have to prove two theorems. Firstly, the fundamental theorem, which relates the syntactic typing judgments to a semantic typing judgment. And what happens here is because semantic typing judgments are really just iris propositions, so there are propositions in our logic, what we have to show actually is that every typing rule becomes a lemma that we have to prove. And in the adequacy theorem, we have to somehow show that semantic typing judgment really implies expression safety. So I have mentioned that in the semantic setting, each typing rule actually becomes a lemma. But to prove this kind of semantic typing rules, we have to somehow be able to reason about programs written in effect. And to this end, we use the program logic of De Villiers and Potier from POPL'25, which allows us to reason about programs with effects in iris. And we extend it to work for programs, to reason about programs in effect by introducing effect rows and also by unify the reasoning about one-shot and multi-shot effects. And this is the end of my talk. Here you can see the contributions again. We have expressive references. We employ a form of bounded polymorphism. And to prove the meta theory, to prove type safety, we built a logical relation, separation of iris. And this whole thing has been formalized in iris and rock. Thank you.
We have time for a few questions. I already see one from Ralph.
Yes, thanks for the nice talk.
Hello.
So I was wondering, in what you mentioned about the optimizations, right? So, okay, if I now have this do choose thing right there, and like I can see choose is a multi-shot thing, I stop doing the optimization. That's nice. But now, what if this is hidden inside a function call, right? Like I could call a function which triggers a multi-call optimization, multi-shot continuation, and the optimization is just as unsound because this is like a function that returns multiple times, which is weird. Yeah. So how do you track that?
Well, I mean, so the effect system tracks any kind of effects they produce, and regardless if it comes directly from a do construct or it comes is hidden behind an abstraction. So that's why, if I understand correctly what you mean, by the function type is denoted by the effects it produces.
Yeah. Okay, that makes sense. So it's not about whether the function does. Okay. Yeah. Okay. I think I get it. Thanks.
More questions? Right here.
Hi, thanks for the talk. This is really cool stuff. I was wondering if, I don't know if you ever said anything about it explicitly, but are there any, is there any performance that you leave on the table by supporting multi-shot continuations alongside one-shot continuations? Are there any things that if you were to do this and only focus on one-shot continuations that you would change, mostly for performance?
It may not be clear here, but there's no implementation involved in this work. It's just a formalized language in Rock. So the whole idea, the whole concept behind motivation, behind optimization, everything are just statements that that are plausible statements on how they can be used. But it's all of like future, how one could use it, not how currently it is. But specifically about your case, I guess that would be a lot implementation specific, but I think not, to be honest, but without giving any concrete specification. I think it's also implementation specific. This.
All right, I will ask one last question while the next speaker gets set up. And my question is also somewhere expressiveness related. OCaml has a letrec construct, which I don't think your formalized language has.
It has.
Oh, it does have.
Well, not specifically in the form of letrec, but, well, actually, no, it's a...
So what
it's very
happens if I write letrec x equals replace label with x?
Letrec, sorry, what is it again? Letrec.
So the replace function
Uh-huh.
takes an argument which is going to be the new thing, and it returns a value which is currently there. If I combine that with the letrec combinator, so I letrec x, which will eventually be the value there, equals replace some container cell with x itself. It seems like the fixed point for that is x is the thing that is in there, and that is still in there.
All right, okay, so in terms of letrec being that, yeah, I mean, this is a call by value setting. So basically, you would just be calling the replace all the time. Well, yeah, you actually would just be calling letrec all the time. You wouldn't even call the operation because it's called by value. So you wouldn't even be calling the replace because you call x. You've tried to evaluate x, and then you'll go into this loop, if I understand correctly.
Okay, that makes sense.
Yep.
Great, let's thank the speaker one last time.
Oh, yes, I forgot.
Oopsie. Test, test. Okay, seems good.
Introduce yourself.
Okay, hi, I'm Daniel. I'm from Aarhus University. I'm going to be talking today about a modal deconstruction of lobe induction. So the starting point for this work is the observation that recursive equations are sort of the bedrock for what we do with denotational semantics of programming languages. They're sort of inevitable and they crop up in most language features. And I've been sort of envious of everyone here having formalized claims in their papers, so I decided to prove this inside of a type theory. Yes, so here is my very short formalized proof that recursive equations are quite useful. But unfortunately, this mostly just leads to the conclusion that recursive equations and dependent type theory, there's something fundamentally in tension, yes? They're simply unsound if we add them naively. But this is irritating because we do want to use recursive equations when modeling things. So there's sort of this cottage industry of constructing limited forms of recursion that we can safely add to dependent type theory. And I want to focus on one of those, and that's guarded recursion. So the sort of thesis of guarded recursion is that recursion is okay to add to dependent type theory, it's sound, provided that we don't have any loops that just spin while producing no output. That prior to making a recursive call, we at least do some sort of work. So we have to crystallize what that means, what it means to do work. And we do that using a modal operator, which is written with this black triangle later. The idea is that later A is supposed to be basically the same thing as A, but you can't get a hold of those values until you do some work. You have to take a step. And the version of the fixed point combinator, which is now sound, is called lobe induction. And it says that if you have a guarded function, a function that goes later A to A, then you can get a unique fixed point of that. So that's later A to A gives A. And the thing to notice here is that now our prior bad proof is ruled out because we're immediately returning proof, but it has the wrong type. It's supposed to have the type such and such, but it doesn't. It has the type later such and such, and these are not the same thing. And there's quite a lot of prior work on guarded recursion, and it's sort of focusing on different ways to sort of slice and dice the integration of later and lobe induction into dependent type theory. So before proceeding to what we're doing, I wanted to give 30 seconds of introduction to what guarded recursion is supposed to be doing. So the intended model of guarded recursion is something like proof-relevant step indexing. This is done using a pre-sheaf model of type theory and pre-sheaves on omega. But if this is not such a comfortable concept, then you can think of types as being families of sets indexed by the natural numbers. And we want to think of them as flowing towards zero with time evolving towards zero, counting down. The idea is that you don't have a value of x, you have a value of x at stage n. And then crucially, the action of the later modality of the black triangle on these families of sets is to sort of shift everything up. So what was stage 1, or stage 0 now becomes stage 1, what was stage 1 becomes stage 2, and the 0th stage now gets filled in with the trivial set, with one element. And now lobe induction is sort of justified just by inducting on the step. So induction on the natural numbers in the model yields lobe induction in the theory. Okay. Yes, look, it's the single object set. All right. So, are we done? Not quite. So the thing is, later as a modality doesn't like to come by itself. It works best with this whole collection of additional type operators that help us sort of refine the behavior of the operation. And moreover, just because later and lobe induction are sound, this doesn't mean that we get a satisfactory type theory out of them. We want the usual battery of meta-theorems. We would like this to have decidable type checking, to satisfy canonicity, and moreover, just to be implementable in some way. Okay? And so into this problem, I propose Gatsby, which is a version of guarded dependent type theory. And the idea is to simply add a lot more modalities than later, but to then remove lobe induction, which turns out to be a rather problematic combinator, we'll see later. So the idea is that we add more modalities, and we add one basic reasoning principle about that one of these modalities, and from it we derive lobe induction. Okay. So about all those modalities. So here's the pictorial representation of all of the modalities that are occurring in Gatsby. I've rendered them as a sort of directed graph here, but I want you to think of them as like a category. So these are the generating morphisms of some category. And in particular, there are actually two very distinct classes of types inside of Gatsby. We have T and S. We call these modes in the paper. And the idea is that types at mode T, those are guarded types. Those are the ones that want to talk about lobe induction, that later acts on, all that stuff. But then alongside them, separately, we have mode S. And these are meant to be just ordinary standard types. No guarded recursion. This is where you prove the theorem that you want other people who don't like guarded recursion to be. Okay. And we have a lot more modalities in this system. So we have L here, which goes from guarded types to guarded types. And this is going to be the encoding in this category of later. But alongside later, we also have earlier, which goes from guarded types to guarded types. And then we have a whole mess of operations which bridge the gap between standard types and guarded types. And these are modalities that encode operations like, given a standard type, give me back the guarded type, which is just constant. It doesn't change as time flows. And then I also have the ability to take a guarded type and give me back the corresponding standard type, which is like the stage 0 version of the type, or I could ask for the stage infinity version of the type. And actually, the novel addition that Gatsby provides is this modality top, which goes from standard types to standard types. And confusingly, all this modality is meant to represent is the operation which sends every type to the unit. This is a bit trivial, but we'll come back to later why this is actually an interesting thing to add to the theory. Yeah? And just to say, there are equations on this category which describes the morphisms, and these are realized in the type theory by sort of equivalences between the modal types. So we write the modal types with these angle brackets and then the letter, just to have some sort of uniform notation. And so the equation that says that earlier after later is the identity boils down in the type theory to an equivalence of types that says earlier later A is the same thing as A. All right. And the good news is that there's been a lot of work on modal-dependent type theory, and even modal-dependent homotopy theory, which is something that will be, or homotopy type theory, which is something that we'll be really capitalizing on in this talk. So it's relatively easy to get an off-the-shelf type theory that has all of these modalities and all of these operations more or less for free. All right, so that's the good news. The bad news is that this doesn't actually help us at all in trying to get lobe induction. You can't just add more laters and more like modal operators to type theory and somehow get lobe induction out, because modalities are too formal. They basically, you can't tell the difference inside the type system between later A and just A. They're distinct in the syntax, but you have models of the theory where every modality is the identity function. So you're not going to be able to get lobe induction out of these things. And actually, the situation is much worse than just that. Because if we add lobe induction as a constant, then we have to decide whether or not we want it to compute, to unfold. And if we have it unfold, this is sound, but it will violate decidability of type checking. And if we don't let it unfold, well, then we lose canonicity. It's just going to be stuck. It's not going to compute anymore. So neither of these two extremes are really that satisfying. We need to somehow strike a middle ground between having it unfold all the time and unfold none of the time. And so prior work on this comes in the form of clocked cubical type theory. You have a fancier later modality, and you use that fanciness to sort of selectively unfold Loeb induction so that it kind of only computes at the top level. But I want to propose a rather different solution. I would rather just not have Loeb induction in the theory and to get it out of somewhere else. So let me move the goalposts, and let's talk about a different proposition, which I'm going to call BOM. So it's written with this font awesome BOM symbol. Okay, so first, advice on reading this proposition, yeah? So the two vertical bars, that's propositional truncation from homotopy type theory. So the propositional truncation of a sigma, it kind of behaves like an existential. So you should read this as there exists some natural number such that later to the n false is true. And the sort of intuition is there are n steps left before things are trivial. And this is true in our intended model. It's not completely obvious, but it turns out that when we're proving elements of an existential in the model, we get to pick different witnesses at different stages. And while there's not a single number for which later to the n false is true, at every stage, there is a number for which it is true. It's just differing between the stages. At stage n, it's n plus 1. All right. And so the intuition for BOM that I want us to carry forward is that it's some sort of like doomsday proposition. It is the very pessimistic belief that the entire theory is about to collapse. We just don't know when yet. Okay? So the idea is that when BOM is true, then eventually everything is going to fall apart at some point that we don't know yet. And the reason to consider this is that it turns out that if BOM holds, then Loeb induction is just provable, right? So guarded fixed points are unique when they exist. And so if we want to prove that Loeb induction is definable, it suffices to show that every guarded function has a unique fixed point. And in homotopy type theory, that type, there exists a unique blah, 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 that's always a proposition. So when we're proving it, when we're trying to construct a map from BOM to that proposition, we're allowed to forget the propositional truncation. And now suddenly we have an actual concrete natural number such that later to the n false is true. And so now we can just perform induction like we would in the model, actually reduce to the case where everything collapses and then inductively build back up. So this is our first use of univalence in the form of Hoth's more semantic notion of proposition that allows us to show that there exists a unique blah, blah, blah is actually a prop. This would also work in extensional type theory. We'll see a more impressive use of Hoth in a moment. Okay, so now we just need BOM to be true, yes? And the issue is that if we just postulate BOM, then we're in exactly the same position we were before, right? We can eliminate the cut and we have Loeb induction, and that's going to make type checking undecidable. However, it would suffice if we can find a collection of types which believe BOM is true without us having to postulate it. So these are types A, such that A is equivalent to BOM implies A. We say these types are accessible. And these are the types that when you're trying to prove A, you're allowed to pull a proof of BOM out of your goal and just use it. And so in particular, if A is accessible, then Loeb induction is definable for A within the theory. We don't need to add it because we're trying to prove an A, so we'll just pull the BOM out of the A and then use that to construct Loeb induction. Okay? Not everything is accessible. If everything was accessible, BOM would be accessible, and then BOM would be true, and then we'd be toast. But it turns out that a lot of things happen to be accessible. This is kind of the happy coincidence of this talk. So we can take a result off the shelf from the literature on homotopy type theory and conclude that accessible types are closed under pi, they're closed under sigma, they're closed under equality, the unit, and in particular, the universe. So a crucial consequence of univalence is that the universe of accessible types, the subtype of the universe spanned by accessible types, is itself accessible. This is great, but we still have no non-trivial base types. And getting non-trivial base types is where we require this fancy new rule. Yeah? So now we return to that trivial modality that I mentioned way at the beginning, this top which goes from standard types to standard types. We're going to add one new rule to our modal type theory. And the consequence of this rule is that the modal type top A is always trivial. It's always actually unit. And on its own, this is very boring. Of course, if we just wanted a type which was the unit, we had the unit lying around. But the important bit is that top was part of this big category at the beginning. And there were equations that related top to other things in our nest of modalities. So in particular, we had an equation that said evaluating at 0 of later of A was top of A. But we've just said top of A was the unit, which means that finally, evaluating later of A at 0 is now trivial. The thing is, I'd like to show the rule at this point, which makes this true, but I've discovered as sort of a matter of practice that if you try and give a talk on modal type theory and you start explaining how modal type theory works, that will be the only thing you talk about. And I don't want to talk about that the entire talk. So you can see the paper if you want to see the gamma and turnstile rules. Okay? I'd rather focus on the consequence of this rule, which is a lot more types are accessible. In particular, the existence of top, together with its interactions with other modalities, and this new rule tells us that accessible types are closed under later, and every constant type is accessible. So in particular, 0 plus bool and nat are all accessible. And so on the previous slide, we had all of the negative types in the universe, and now on this slide, we have all of the positive types. And so the consequence of this is that we can take normal guarded type theory with all the normal operations, normal connectives, Martin-Love type theory, that sort of thing, and interpret it into Gatsby and compile Loeb induction in that standard guarded type theory to our definable version of Loeb induction. And in particular, a user basically never encounters a non-accessible type. They do exist, they just don't come up as much. And the consequence of that is that when you're programming in Gatsby, you just get to kind of pretend Loeb induction exists. And you get to never talk about BOM in particular. Okay. So that last claim is something that one has to test a bit, that when you actually use Gatsby, it's, you don't end up manipulating the BOM proposition yourself. Ideally, this is the part where I'd say we have an implementation of modal type theory and I tested it in Agda, but we don't have an implementation of modal type theory yet that's sufficiently flexible to support all these modalities. And so instead, we have LaTeX. So I've carried out some pen and paper case studies and redone some of the classical results from guarded recursion, step index logical relations, co-inductive types, and I found it to be a highly usable system. All right, so for the sake of time, I'm going to skip forward here and just say that that was Gatsby. So it is a new approach to guarded recursion, which is modality-centric. We had a lot of modalities. We had one new principle about those modalities, that top of A is unit, and from it, we derive the essence of guarded recursion and Loeb induction. Thank you.
We've already got a lot of questions. I see Bob.
Just a quick clarification. Did you say you have a whole class of inductive types, or you just listed specific ones? I wasn't sure. Like you have an inductive type constructor of some class of inductive types that you can do?
Any inductive type which doesn't use, so any inductive type in standard type theory will lift to an accessible type. If you start invoking other guarded types, then it becomes more subtle, but it's still closed under a lot of operations. Yeah, like you can have lists. Everything is okay. Yeah.
Do we still have a question over here? Same question. More questions. So while the next speaker sets up, I'll ask you to do something that I think you might have had a backup slide for, so sorry about this. Can you say more about the meta theory of your system?
Right. So let me unplug here. So of course, the big question is whether Gatsby also satisfies normalization and canonicity. And the thing is, because it builds on cubical type theory and modal type theory, this is quite an intricate theorem. So what we can prove is that modal type theory sans the cubical stuff with this new rule satisfies normalization and canonicity. That's fine. The issue is that in order to prove that the entire system does, we also need to integrate univalence in a computational way. And this involves fusing two very intricate proofs. So future work is to show that the actual total system, the fusion of everything, works. All right.
Great. So let's thank the speaker again. And now we'll have Li Tao from Hong Kong tell us about QuickSub. Take it away.
Yeah, thanks for the introduction. Hi, I'm Li Tao, and this is joint work with my advisor, Bruno Oliveira, the University of Hong Kong. So this work is called QuickSub, which is an efficient algorithm for subtyping iso-recursive types. So let's start with some background on recursive types. We know that recursive types are useful for defining recursive data structures, like objects, So with this syntax of recursive type in your type language, you are able to represent formally, for example, a class object that is self-recursive with a recursive record type. And there have been a lot of studies on formalization of recursive types. And there are mainly two flavors, iso-recursive types and equi-recursive types. And our focus today is iso-recursive types. So one important feature of iso-recursive type is that it does not treat recursive types and their unfoldings as equal, but instead you need to insert this explicit term level unfold and fold constructs to convert between terms that are of recursive types and their unfoldings. But still, you can have subtyping between iso-recursive types if your two recursive types have the same levels of unfolding. Iso-recursive subtyping have a few advantages over equi-recursive types or subtyping. The first is that you don't have to do co-inductive reasoning with the type equality definitions as seen in the equi-recursive types, so it usually gives you a simpler meta theory. And that also makes it easy to extend iso-recursive subtyping to more advanced type system features like recursive modules or bounded quantification and so on. And another benefit is that with iso-recursive types, you get more efficient meta operations like equivalence checking. But one missing gap that we've noted in our work is that there currently is not a efficient algorithm for subtyping iso-recursive types, and that motivates our work called QuickSub. So before I introduce the technical details of QuickSub, let's first take a look at some examples to get some considerations for what types can be in this iso-recursive subtyping relation. So the property here is kind of expected for iso-recursive subtyping, which is usually called unfolding lemma. That is essential for type safety if you want to have a calculus for iso-recursive types. So it states that if two recursive types are subtypes, then their unfolding should also be in a subtyping relation. So the first observation is that positive subtyping, which means that all the recursive variables appear positively or more intuitively to the right of function arrows. For this kind of types, it is easy to check. You can just compare their type body. So these two types are subtypes. And you can check that by doing one-time unrolling, two-time unrolling, and you will see that all the comparison you get is between this top type and integer type at a contravariant position. So that holds. But negative subtyping in most cases has to be rejected, like these two types. And you can check that by, so one-time unrolling is fine. You get int less than top. But if you unroll it two times, you get a contravariant comparison in the which requires that top to be a subtype of int, and that does not hold. So you have to reject this pair of subtyping. But there are also exceptions to negative recursive types. For example, you still expect reflexivity between these negative types. And also, if you have top types in your recursive type, it is sometimes fine for these two types. And you can check that by doing an unrolling, and you will see this negative occurrence of the recursive unfolding is subsumed by this top type here. And the problem of iso-recursive subtyping can get even trickier if you have nested recursive types. So these two types seem to be subtypes if you just look at their body, but actually they are not, and you can check that with the unfolding lemma by unrolling alpha and beta at the same time. So with all these considerations, perhaps the most widely used rules to subtyping iso-recursive types is the Amber rules proposed by Cadelli back in the 1980s. So the Amber rules basically introduce a special context that allows you, when comparing recursive types, you can introduce an assumption that the recursive variable of the first is the subtype of the second into the context, and then you can compare the recursive type body. So with the first two rules, you are able to deal with these positive subtyping cases, as well as ruling out these problematic negative cases. But these two rules cannot account for reflexivity. So in particular for negative subtyping, so in order to get reflexivity in your subtyping relation, you will need this extra amber self rules to allow reflexivity. And that gives you an efficiency concern if you want to implement the amber rules, because you essentially need to do backtracking on these two rules when you compare to recursive types. And that can be costly if you are dealing with nested recursive types. And another efficiency concern is that the amber rules require these recursive variables to be distinct in order for this rule to make sense, which is a non-trivial requirement in practice. And if you're not dealing with recursive types that satisfy this assumption, you will need extra runtime overhead for renaming. So with these inefficiency concerns with the amber rules, our work proposed QuickSub, an efficient algorithm for dealing with isorecursive subtyping, and we prove it to be equivalent to the amber rules. And for the rest of this talk, I'm going to use this notation, although it is written in a judgment form, but it can be interpreted as an algorithm by treating this context, polarity mode, which I will explain shortly, two types as input, and also we change this. We introduce a meta variable that can be ranged between strict subtypes or equivalent result as also part of the judgment, and you can treat that as output. So this notation is no longer part of the subtyping judgment, but rather it's a meta variable of representing subtyping result, and you will treat it as a output of an algorithm, and our algorithm will actually return failure if no rules apply. So as you have probably noticed from the design of these notations, there are actually a few key ideas in QuickSub. The first is that we are tracking polarities by introducing the polarity mode that can be either positive or negative to all the variables in the context, as well as the judgment form itself. So when you compare two recursive types, you will introduce the recursive variable into the context, as well as the current polarity mode. And when you go into the contravariant case, when you compare function types, you will flip the mode of the judgment. And this implies that if you end up with a variable that is you need to retrieve from the context that has the same polarity as the current judgment polarity, then that indicates the current alpha is positive at that point. Otherwise, it's negative. So this gives us an efficient design of tracking all the polarities efficiently in the algorithm. Another idea is that our algorithm now distinguishes strict subtypes from equivalence all over the judgment. So this can be implemented by first precisely tracking these base cases, and then compose them where necessary. For example, in the function case, you only get equivalence from composing two equivalence results. Otherwise, you get strict subtypes. And by treating the positive variables to be considered as equal, we are now able to deal with the positive subtyping examples from our first observation. But as I have said, the trickier case is negative subtyping. So now let's deal with it. The goal is to, we want to check subtyping by directly comparing the type body. We do not want to introduce extra rules that requires backtracking, renaming, or unfolding. So actually here in the design of QuickSub, we make a more general observation from the example that when negative recursive variables are compared with themselves, they essentially create a constraint that the recursive type they correspond to should be equivalent. So let's consider this invalid example we have seen before. So it fails because at the end of the derivation, you are comparing alpha in a negative position with it itself. And that contradicts with the fact that what you get from the type body is not an equivalence result. So that caused the subtyping to fail. But if this alpha, although appearing in a negative place, but it's not compared to itself, but top type, then it is still fine for the subtyping relation to hold, like for this example. So with this observation, we are able to deal with negative recursive subtyping. And in the implementation, to capture this idea, we introduce what we call equality variable sets, which are annotated to every equivalence result that captures these constraints. So for positive variables, they don't create these constraints, but for negative variables, you will need to add the current variable to the constraint set, so that later, when you can, for example, in the function case, we are now requiring that every time you compose an equivalence result to a strict subtype result, this constraint set, equality constraint set, has to be empty. Otherwise, it will immediately fail the subtyping check. So with this design, we are able to disprove such negative subtyping examples. And also, although you have this equality variable sets, you can still propagate equivalence results from type bodies to their to a recursive binder, except that you essentially need to do some bit of rewriting of the equality variable set here, but I don't have time to explain that. You can see our paper. Basically, we design a rewriting strategy for this equality variable set so that our algorithm can also handle a nested recursive subtyping in a correct way, in addition to ensuring reflexivity. So that's basically all the ideas in the quick sub design, and you can see this quick sub can actually be implemented in a functional style, and you can check all these cases are disjoint from each other, so you do not need to do backtracking. That gives you a linear traversal of the that is of the size of the types. But we do have a little bottleneck here, which is the set operation that you need to do in order to ensure correctness, which is on the equality variable sets. But in our implementation, we can optimize them using imperative data structures. So the basic idea is to update it on the fly and when you're doing the subtyping checks. And that will give us a linear cost, which is in terms of the number of total recursive variables in the worst case. But we will show that for practical case, this is often a constant complexity. So overall, QuickSub has a OMN cost in the worst case and linear for practical cases. So in order to check our claims here, we actually performed an evaluation in our paper. So we implement QuickSub in OCaml, and we compare the performance of QuickSub with other existing algorithms, including the Amber rules, as well as nominal unfolding rules, which are recently proposed that have proved to be equivalent to the Amber rules, but addressing meta-theory challenges. And although nominal unfolding rules are algorithmic, but they are not designed with efficiency in mind, as we will see later. And we also compare to the complete isorecursive subtyping work by Ligati and other authors. And their rules are more expressive than the Amber rules, but in their work, they actually do implement an efficient OMN algorithm. And in the paper, we also compare to equirecursive subtyping. So we evaluate all the examples, all the algorithms on examples that we come up with to capture the different recursive type patterns you would normally encounter when you are doing programming. For example, in practice, you may write these nested recursive objects, and we use this kind of patterns to do our evaluation. And you can see that as the depth of the recursion goes get large, so for this positive nested recursive subtyping pattern, the Amber rules and the complete algorithm are actually quadratic or even worse in terms of complexity, but our QuickSub remains linear and efficient. And in the paper, we have more patterns to evaluate different patterns benchmarks. And here I just visualize them using a bar chart, and you know that the time scale is logarithmic. And the results show the QuickSub outperforms other algorithms in most cases, except those reflexive cases, because we implement the Amber rules in a way that it always tries reflexivity before backtracking. So in these cases, reflexive cases, the Amber rules will perform faster, which is kind of expected. And overall, the evaluation shows that QuickSub handles both simple and nested recursive types efficiently, and that gives you linear performance in practical scenarios. And one interesting case might be the worst case pattern. And the worst case scenario actually only occurs here when all the variables are negative and the subtyping and the two types in your subtyping relation is equivalence, so that you need to frequently operate on the equality variable sets and maximum size of the equality variables set is the number of recursive variables. So that, as we have shown, the complexity is OMN. But since we have this imperative structure of, in our algorithm implementation, this optimization, QuickSub still demonstrates an efficient performance compared to other algorithms like the complete rules. So to conclude, we present QuickSub, an efficient algorithm for ISO recursive subtyping with linear complexity in practice. And you can find more in the paper about, we do have a mechanized rock proof that shows equivalence to other ISO recursive subtyping formulations, as well as a type soundness proof for calculus using QuickSub. We also extend our algorithm to support record types to give more evaluation examples, as well as a demonstrator of scalability. In the future, we plan to extend QuickSub to handle more type system features. And also, we're trying to deal with equirecursive subtyping using these ideas. So that's all for my talk. Thank you for your attention.
Okay, questions?
Could you talk more about the extensions that you're thinking of? So for example, if we want to add just union types without any distributivity, would that be a trivial extension, or does adding new features really make sort of calls for extra, I don't know, handling of polarities or something like that?
Yeah. So I think we can decompose your question step by step. So for union type or intersection types, I will expect it to be easy because although you cannot avoid backtracking when you're doing intersections and unions, but you can still apply this idea to kind of avoid unfolding or backtracking for recursive types. And in terms of distributivity on union types and intersection type, I'm not sure if that's what you meant. The problem itself, I think, is already kind of tricky. And there are actually, I don't think in theory they have a good, so maybe the first step is to think how, before the algorithm, to think about the rules. And so, yeah. Okay, yeah. Since in our group, we have a work on combining this formulation with bounded quantification using nominal unfolding rules, I briefly mentioned. So we're considering, in that case, how to implement QuickSub with bounded quantification efficiently. Yeah, thanks.
More questions? I feel like I saw a hand, but then it went down. Oh, no. So I have a quickly naive question while the next speaker gets set up. I'm used to a formulation of the Amber rules with only two judgments, which lacks the reflexivity judgment. This is obviously a limitation for expressiveness, but what I'm not quite sure of is what sort of compelling programs will fail the type check under this more restricted Amber set, which will be allowed with the presence of the reflexivity rule, which is also your source of complexity.
You mean that the Amber rules is, sorry, can you repeat the?
Yeah, sorry. Once upon a time, I read Types in Programming Languages, and in that book, the Amber rules are presented with two rules.
Yeah.
And they're missing the reflexivity rule.
Yeah.
That formulation doesn't have any of the computational complexity, but it gives up a little bit on expressiveness.
Yeah.
I'm wondering if you can comment on, a particular example program or type of example program that we would want to type check, but would fail to type check without the reflexive rule.
I think the reflexivity is kind of expected. Otherwise, you'll get other problems. I'm not sure I'm completely understanding your question, but yeah, maybe we can take that offline.
I did say it was a naive question. Let's thank the speaker one last time.
Thank you.
Where's those? Is it? Hi, everybody. It's my pleasure to welcome you to this second session of POPL on program logics. So today we have in this session we have three great talks. The first one is going to be Bicycle by Joris Kelmans.
Yes, thank you. So let's see. I mean, what's better to digest our lunch than talking about modalities in type theory? So let's do this. Right, so if we have a type theory, well, we typically prove its soundness by constructing a model of the type theory. And the most famous one is a set model, where we just interpret types as sets. But there are plenty of others. For example, we have the topos of trees, we have cubical sets, etc., etc. Now, as a general notion of model, we will take a category of families, or a CWF, but it's not really important to know what that is in this presentation. But let's say there's just a general notion of a model of type theory. So we could have several models of type theory, and then we have interesting functors or morphisms between them. For example, we can consider the later functor on the topos of trees. Now, an interesting question is, how can we internalize these morphisms? So how can we, in other words, extend a type theory with constructors that will eventually be interpreted as these morphisms? And it's exactly that kind of type constructors that we will call modalities in this presentation. So why would we be interested in this in the first place? Well, such modalities can extend the expressivity of a type theory. More concretely, via modality, we can express certain aspects of the behavior of a function in the type of that function. So for example, we could, using a modality, express that a certain function is parametric or that it's irrelevant, or we could use a modality to express the recursive behavior of a function, and then we get to guarded recursive type theory. Now, in the literature, there's a lot of work on how to add modalities to type theory, but most of these papers, they consider a single application, and then they consider just the modalities that are necessary for that application. And in order to unify many of these systems, Daniel Gratzer and co-authors, they developed what they call multimode type theory, or MTT, which is a general framework for modal type theory parameterized by a mode theory. And so the mode theory captures the entire modal situation. And so it consists, among others, of a set of modes, and these modes will, in the model, correspond to these different CWFs. And it also consists of modalities, which will then correspond to the morphisms between these models. And if we then instantiate MTT by a concrete mode theory, then we get an entire modal type theory that can then be used to program and prove with a certain modal application in mind. Okay, but if we really want to work in MTT, if we really want to write programs and proofs in it, we need an implementation. And at first sight, there are two possible approaches for obtaining an implementation of MTT. Either we could extend an existing proof assistant and add support for modalities to it. The advantage of this is that such an existing proof assistant already has a user base, already has some interesting features that we can use to write programs. But on the other hand, we are extending the proof assistant, so it could in fact be that we end up with a system that is unsound. Then, as a second approach, we could also just start from scratch and develop an entirely new proof assistant. The advantage of that is that, well, we get something that is very suitable for programming in MTT, but of course there is then no existing ecosystem. And there has been work in these two directions already, so that has been, there has been work on this. But actually, and what I want to talk about in this talk, is a third alternative approach, and that's based on the idea that type theory can eat type theory. So we can use type theory to formalize type theory. And then the question is, of course, can we also use type theory to formalize MTT? Because if that's the case, then our approach could also be to write a library for MTT in an existing proof assistant. And so that could have some nice benefits. For example, we would be working in an off-the-shelf proof assistant already, and soundness would be by construction because we are actually just implementing a library in an existing proof assistant. We're not extending a proof assistant. And then the third point is this library approach allows us to kind of modularly use modalities. So what do I mean by that? Suppose that we are working on some, for example, AGDA project. So no modalities involved at this point. And then at some point, we discover that we need guarded recursion to write a certain function. We would then instantiate our library with a mode theory for guarded recursion, and then we could use the primitives for guarded recursion to write our function, and then we would somehow hope that we can extract this function to get a normal AGDA function that we can then use further on in the project. And then if at some later point we discover that we need, for example, parametricity to prove some property, we can instantiate our library with a mode theory for parametricity, use the primitives there, and also extract the proof to get a normal AGDA proof. So we actually, with this library approach, we only use our library when we need the modalities, and for the other parts, we just use normal AGDA. So the question is, of course, can this be done? And so a couple of years ago, we gave a positive answer to that question for a simply typed fragment of MTT. So there we implemented our SYCL library in AGDA. And so SYCL consists of, well, 3 layers. So the first layer is a syntactic layer, and that is a formalization or an encoding in AGDA of what we call multimode simple type theory, so, or MSTT. So that's a simply typed fragment of MTT. We can instantiate that with a mode theory and then write modal programs in it. Now, SYCL also consists of a type checker, and the type checker is sound by construction, which means that whenever it decides that a program is well typed, it will also output the denotation of that program in the semantic layer. That semantic layer is a formalization of pre-sheaf models in AGDA. And then we have this extraction mechanism that I told you about. So that allows us to extract the denotation of some programs to ordinary AGDA functions, and I will specify a little bit more details about that later in the talk. Okay, so that's all nice, I think. So now we can write modal programs in our library in AGDA. But of course, well, we are at POPL. We saw yesterday in the business meeting that verification and proof assistance are popular topics here. So we do not only want to write programs, we also want to prove properties of our programs. And unfortunately, with simple types, that's not possible. And so therefore, in this work, we present Bicycle, which adds a logical framework, a multimode logical framework called MuLF on top of SYCL. And this multimode logical framework can be used to reason about MSTT programs. We also provide a soundness proof and a proof extraction mechanism, which I will talk about later. And by implementing this, we also made some major reworks on SYCL, so most notably on the MSTT representation and program extraction, but that's also something for later. Right, so let's make this a little bit more concrete by considering a particular application of modal type theory, namely guarded recursion. So here we have an AGDA function that takes a function f from a to a value a, and produces a stream of a's, namely the stream a, f of a, f of f of a, etc. And how can we implement this? Well, we could implement it as follows. So we say the first element of that stream is a, and then the tail is obtained by mapping f over a recursive application of iterate fa. And if you try to write this in AGDA, then AGDA's productivity checker will complain and say, well, this definition is not productive. But actually, if you stare at this for a little bit, well, I don't have the time to do that right now, but if you stare at this a little bit, you see that this definition actually is productive. So AGDA's productivity checker is wrong. Now, how can we solve that? That is, well, one possibility to solve this problem is using guarded recursion. So guarded recursion adds a later modality to our type theory, which is a unary type constructor. And then we can see that, well, we can construct a type of guarded streams, and a guarded stream of A's has a head of type A and a tail of type later guarded stream of A. And also, the final thing that guarded recursion adds is a fixed point operation called loop induction. So in order to produce a value of type x, we need to produce a function from later x to x. And this later will make sure that every fixed point, well, every definition is productive. And using these primitives, we can then, we can then use our library to write this iterate program. So that's what it looks like in the syntactic layer of Bicycle. I will not spell out the details, but you can see what it looks like in Bicycle. Now, actually, we could also implement this iterate operation in a different way. We could also just say we get this iterate prime here, that the head is again A, but the tail is iterate prime of F and F of A. So now we have two algorithms that should compute the same stream. Can we actually, well, prove that they compute the same stream? Well, we can start by taking iterate FA, expanding its definition, and then, well, it's a pretty, well, we can show a lemma that mapping F over iterate FA is, will get us to iterate F of A. I will not show that proof here. And then we would hope to apply an induction hypothesis. So then we could say, okay, now we're in the tail, and in the tail, iterate is equivalent to iterate prime. And then we're just back at the definition of iterate prime. So that was not too hard, but of course the question is, can this reasoning be made sound? Is this indeed something we can do? Especially this induction hypothesis. And so an intuition for why we can use this induction hypothesis here is because, well, the tail of a guarded stream appears under a later modality. We've seen that via loop induction, constructing a value of type X, we can assume something of type later X. And so indeed, well, if we have some variant of loop induction for proofs, we would be able to do this. But that means that we need to apply later to propositions. And so that really means that we need a multi-mode logical framework to reason about MSTT programs. So what does that then look like? Let's take a little look at what MuLF looks like and how it's implemented in Agda. So here we see that there are two Agda data types, one of propositions and one of proofs. The idea is that MuLF is a subset of MTT. So we can see these propositions as actually dependent MTT types, but they are only allowed to depend on program terms. So actually we have a stratification of MTT into a simply typed fragment and then a dependently typed fragment where we only have types that depend on the simply typed terms. And so here we see then that this B-prop for bicycle proposition is indexed by a context that can just contain program variables. And we see that there are constructors, for example, to express that two MSTT programs are equal or to apply a modality. We also have our data type of proofs, which is also indexed by a context, for example, for providing reflexivity proofs. Now, in this way, it's possible to write invalid proofs. And so Bicycle also has a proof checker, which comes in the form of an Agda function check proof. It takes a proof context. Proof context can contain not only program variables, but also proof variables, so assumptions. It then takes a proof, where we just, well, this 2ctx function, it just removes all the proof variables from our context, and it takes a proposition, and will then tell us whether P is indeed a valid proof of phi. Not only that, but when it decides that indeed this is a valid proof, it will give us the denotation, well, it will give us some evidence of that fact by constructing a semantic term in the pre-sheaf model of type the interpretation of phi. So indeed, this proof checker is sound by construction. Now, to implement this, we need some more infrastructure. Well, we need to expand and modify some of SYCL's infrastructure. First of all, we have an intrinsically typed representation of MSTT terms. So here we see that the terms are indexed by a context and a type, which means that it's actually impossible to write terms that are not well typed. We also expanded the pre-sheaf formalization layer of SYCL. We proved many new coherence laws. We implemented a few-word normalization algorithm, which is also sound. So when it does not only return a normalized term, but also a proof that the denotation of that normalized term is equivalent to the denotation of the original term. And we also implemented a substitution algorithm that we described earlier, and we proved that it's sound with respect to the pre-sheaf model. Okay, and then the entire proof looks like this. I will not go into all the details, of course, but I want to note that the first few lines are the proposition we actually want to prove. Then the majority of the slide here is the actual proof. That seems like a lot of code, but actually we can see that these are just the four equality steps that we saw in the previous slide. And then the last two lines, the fact that those type check means that running our proof checker on this proof is actually successful. Okay, let me tell you a little bit about this extraction mechanism. So recall from the first slide that we have these models of type theory, and one of these models is the set model. And so that means that in our, and so recall that all of these CWFs correspond to modes. And so suppose now that we have one mode that gets interpreted as the set model. That means that types at this mode are interpreted in our formalization as just AGDA types, and terms are interpreted as normal AGDA programs. And that means that such programs are very easy to extract to an AGDA program because their denotation already is an AGDA program. And so that's the idea of the extraction. Extraction is only possible from this trivial mode. And what happens if we have a program at a different mode? Well, the idea is that you then first need to apply a modality to get to that trivial mode. We reworked the internals of this mechanism with respect to SYCL. So this mechanism was already there for in SYCL for programs. We reworked the internals, and we also added a proof extraction mechanism. So that allows you to extract proofs. Now you get normal AGDA proofs about extracted MSTT programs. Unfortunately, due to type checking performance, that doesn't work for this iterate example, but we have shown it to work for more trivial examples. Okay, finally, something about the design choices of our library. So first of all, we have intrinsically typed programs. So recall we made MSTT intrinsically typed, but extrinsically typed proofs. Intrinsically typed proofs would mean that we encode all the proof rules in the data type of proofs, so that we cannot write invalid proofs, but we have seen that we need a proof checker, so in Bicycle you can write invalid proofs. We've tried to come up with an intrinsically typed encoding of proofs, but unfortunately that makes it, performance issues then occur when we try to write actual proofs. A second design choice is that MuLF, our logical framework, is a strict subset of MTT, and that allows us to reason in a modal setting without having the complications of interpreting type theory in type theory. Why complications? Well, basically you have two options. Either you could use intrinsic types, but then it becomes very hard to write programs, or you could depend on extrinsic types, but then it becomes very hard to state the AGDA type of the type checker if you want soundness by construction. And so to wrap up, I presented Bicycle, which allows multi-mode reasoning as an AGDA library. It works with arbitrary mode theories. There is also another example in the paper. We have moderate use of modalities, sound proof checking, sound program, and proof extraction. And there's also some future work, but I'm told to wrap up. So thank you for your attention.
So we have time for a few questions. Perfect.
Hi, Max New, University of Michigan. Considering these performance issues, to what extent do you think that they could be addressed in the implementation, or that they really need to be changes to AGDA itself to address these performance issues?
I think so I'm not really aware of what the source, like the real source of these performance issues is, but I assume that you would need to rework AGDA in some way to resolve them, or try to work out this library idea in another proof assistant. So yeah.
I find this idea of embedding a logic, domain-specific logic, is something you see all the time at POPL. We develop the domain-specific logic. We want to get out the actual semantics, basically like what Iris does, right? Generalized, right? But we need to figure out what are the actual features we need and performance we need from AGDA to be able to do this more effectively.
Yeah, agree. Yeah.
Hi, I'm Anthony from University of Illinois. Thinking about this proof extraction to set. I'm wondering, from a theoretical basis, what are the obstructions to extracting to a different mode, something a little more complicated than set?
I think there's not. So that would mean that you get like a different presheaf category. So there would not be like theoretical obstructions, other than I think the obstructions would be more practical. So I think what's very nice here is that you really have to use the modalities to go to the trivial mode. So everything happens at the syntactic level. But of course, if you're more familiar with how the pre-sheaf semantics works internally, you could actually leverage that. But the point here is that for the application that we studied, you could just use the modalities for that, and you don't actually need to bother. Yes.
Okay, let's thank the speaker again. And so our next talk is going to be by Patrick Couzeau, who's going to tell us how to obtain hyperlogics, of course, by abstract interpretation.
My co-author is somewhere. Where are you? He's there. So interesting co-author. You should ask him questions. So let's go. We want to have a method to design hyperlogics. So you have to understand what is the semantics, what is the strongest property, what are the properties you are interested in, and then you derive the other one by consequence, and then you ask what are the proof rules, and I have the answer last year in the POPL paper. You start from a relational semantics, you identity to collecting, then you have some abstraction that go through the theory, and then Axel, Parks, and others goes to the rule. What is interesting, if you start by a structural fixed point definition, the calculus gives you all along the way structural definition, and so at the end, the logic will be by structural induction plus some argument for inductions. So the methodology is to calculate hyperlogic by structural abstraction of the program semantics. So I go to the conclusion, can we do it? Yes, but the problem is there is no abstraction in hyperlogic. So if you want to think something which is sound and complete, it's completely unmanageable. And the other way around is abstraction. And so I will follow this path plus at the end abstractions. So with semantics is interesting because when you have all logic, you think it's for invariant, but assume you instead want history, that is, what are the paths that arrive at each point? Intuitively, the OR logic is the same. Unfortunately, you cannot apply OR logic. And this is because of bad choice of the semantics, which was relational last year, and this year is better. It's an algebraic semantic. So what is an algebraic semantic? It's parameterized by a semantic domain, which is built out of two things. One is this set, which is description of executions. That is, semantics define properties of execution. So this is a finite one. Then you have implication and so on, union for handling if then else, and you have primitives. And another one is for infinite executions. And then your semantics will be three things. One is, for example, the assignment, how I go on after terminating, so this is a primitive. How I can escape using this assignment, it's impossible. How do I do not terminate with this assignment? It's impossible. It takes a break, you cannot go in sequence, you have to break, and you always terminate. So now what is interesting, and the only problem, is the iteration. So I define this operator. I want to know what is the semantics when I iterate in a loop and come back at the head. So there are finite execution. You say there is 0 iteration or 1 iteration followed by n-1 iteration. This is the backward one. There is also a forward which says it's either 0 or n-1 plus 1. So they are equivalent. Then I have another operator. So I will use this with induction, and this one with co-induction. You don't terminate if you make an iteration and then don't terminate. Then I can define the semantics of the while. How do I go terminate and go in sequence? I iterate and come back to the loop head, and then suddenly the test is false, or I start an execution of the body that does not terminate, that breaks, excuse me. I terminate by the test or by a break. So how can I use a while to break another external while? It's impossible. And here I consider how do I terminate when the body always yes, when I do a number of iterations and the body does not terminate, or the body always terminates, but I do it forever. So this is the semantic of non-termination to these two cases. Okay, we did. So it's algebraic because if I apply the paper of last year to these semantics, I get the classic paper on algebraic semantic, except that it is for an instantiation because they use states and so on. It's an instantiation of this. Okay, so now we have how to express properties. In logic, program logic, you have a language for program and a language for logic. And I've got a great idea that I took from Henner, which is we are only interested in program properties, so program properties can be encoded by a program. And this is the same idea as the two guys here who in their paper said program properties are recursively enumerable. So if they are recursively enumerable, there is a program that generates them. So we can define properties as program, and we have only one language. And then the others are abstraction. So now we need a property transformer, which is post. So post, you say, assume P, execute S, and then post will be true. What is it in terms of program? I execute P, so at the end I will have the properties of P. Then I go on in sequence execute S, and then at the end I have the property of S when P. So we have the property transformer, and you can give a structural characterization. And this is the POPL paper of last year, except that now we have an algebraic semantic instead of a relational semantic. So you get the little q plus 2 points with the next talk. You get everything. Not interesting, so I go on. Now we move with hyper properties. And what is an hyper property? You have some semantic domain, in my case, termination, non-termination, and break. You put that in the triple. This gives you the semantic domain, and you take the power set, and you get hyper properties. The inclusion is implication, and you have a complete lattice structure, which is very nice. Okay. So we need to define an hyper property transformer. This is this one. You said you get an hyper property, you take any property inside and you push with the property transformer and you take the set of all these guys, and this is a Galois connection, so you think it will work. Then you try to have a structural definition of this operator and you get a problem. And here the problem, I want to define the pose of the conditional, and I would like to say, like in all logic, I take the pose in the true case, I take the pose in the false case, and I make the join of the two. But it does not work. You see, you expand this definition, you expand this one, and you see here it's the same, it is the same P, whereas here it's different P's. So this lose the links between the property in the hyper properties. So many people say I take equal. This corresponds to an abstraction which is described in the paper. And so if you define the logic from there, it's always sound. But if your property is not closed under this abstraction, you are incomplete. Okay, so we have to find a workaround. It's very simple. If you take the pose of a singleton, it is a singleton of the property pose. So now I can rewrite this like this, and I take the singleton, and I get an equality. So we have a structural definition of pose, hyperpose. We apply paper of last year. We get a logic, and you over or under approximate, okay. And then this is the rule for the while. Don't read it, it's horrible. But what is interesting is if I have an hyper property, I execute, this one will be true. I want to prove that, and because it sounds incomplete, it's only if I can prove that. And there you see I have to find a guy which is exactly describing how you come back at the end of the loop, at the head of the loop, and here you have to find a guy which exactly describe when I do not terminate. And if you make any approximation on one state, it doesn't work. So we have a logic which is not manageable, but sound and complete for any program property. So when you have a non-manageable computer science, you do abstraction. I'm lucky to have at least one that understands that. Huh? So remember, you went from algebraic semantic to program properties to hyper properties to logic. So we can do an abstraction at this level. For example, I had the semantic with traces. I go to relational semantics, and I get an abstraction. Or here, for example, I had hyper properties here, and I do the union of the hyper properties inside, and I get the classic properties in all logic. Or you can do an abstraction here. And so this is the main contribution. So yes, the first one is if you do, excuse me, I forgot something. If you do an abstraction here, it propagates here. If you do one here, it propagates here. And so at each level, there is possibilities. And the interesting thing is if you do an abstraction of the semantics, it is still another instance of the algebraic semantics. So that's why it's true. Okay, so let's go to hyper properties. There are a dozen in the paper, many done by Jeffery. And we have a lattice of all properties, which someday will be a cube, I'm sure. And if it's a cube and you are popular, if not a cube, no one remember. So, so I will describe this point here. So it's a chain limit order ideal abstraction. Very nice. What is it? In fact, it's a generalization of for all exist abstraction. So the for all exist hyperproperty. It is for traces. So you instantiate my complete lattice that I have at the beginning to set of traces. And then the for all exists are hyper properties, as a set of state that are so that if you have any trace, there exists another one which is related according to some relation. So that's the general definition. Okay, forget about this and consider the abstraction. The only problem is loops. So if you have an hyper property P, and you imagine I have some property for the first iteration, another one for the second, for the third, and so on, and you have no way to say, to pass to the limit, then you are in trouble. So we say, okay, we consider the cases where you can pass to the limit. And then you have so this is a closure operator. And we take this one, which says, when you have a property, we consider all the one below. Why? It's because when you iterate to this fixed point, you start anywhere from below, you will reach this fixed point. And so now you have solved the problem if the function is continuous. Because infinitely many iterate, you have it. But if it's not continuous, and this is the case here, when you compose these two guys, then the operator, they are just extensive and increasing, and so not idempotent. And so you have a problem because if it's going higher order in the iteration, you will not make it. So the solution is very simple. It's a theorem I had in the I don't remember. It's a Portugalia Mathematica. And so you take the fixed point of this. So essentially, it means iterate infinitely many often, take the lub, reiterate infinitely many often, take the lub, reiterate, and so go in the hierarchy of ordinals, and at the end you will converge, and this will be the operator you want. So this is a Galois connection. So you apply a POPL of last year, and you get the logic. And what is interesting is that if you instantiate for traces, then you get the always exist hyper properties. And so because we have a logic for reasoning on that, we also have a logic for reasoning on that for the specific case where the semantic is set of traces. Okay? Conclusion. So my standard conclusion is we are the best. So, so I have to prove it. So, so we have introduced a new algebraic semantics. We have that. We have considered the program as properties. Okay. We have designed by everything by the method of last year. Okay. And we have a general algebraic hyperlogic sound and complete, but no one will ever use it. And we have This includes terminating, non-terminating things. And so at this point, we did some abstractions. And if you consider an abstraction of the algebraic properties, they are less expressive. You limit what you can say, but you can get a sound and complete logic to handle this class of hyperproperties. And we illustrated that by for all exist. And then my co-author said, yeah, but you have forgotten 3/3 of the paper. Okay, so yeah, in the paper, many other things, various instantiations of the logic, many abstraction of the hyperproperties I have shown, including exist for all and for all exist, which my co-author is very proud of. Okay, so also he corrected a few errors that he found in the literature, and he was happy. So now I have a conclusion of the conclusion. If you do not read the paper and understand nothing in the talk, you can always remember that a transformational OR logic is an abstract interpretation of an hyper-transformer of an instantiation of an algebraic semantics. It's already hard to remember that, huh? But, but you can also have the inverse, which applies to the previous talk. You see, it says, people that say, oh, I can do nothing, I will define a logic. So they start from saying, I have this rule, this is a logic language. And so what are they doing? They define an hyperlogic or logic, which is a complicated way of defining an abstract interpretation of an instantiation of an algebraic semantics. And why is it complicated? Because the rules don't tell you the whole truth. For example, you have made an abstraction, it doesn't tell you what it was. You have used an induction principle, it's hidden in the rules. You want to prove that two proof methods are the same, what do? We say, oh, they do the same abstraction, so they are the same. Whereas they have to prove any proof in the one, I can do the other proof, or the other, I can do the first. And so reasoning on proof system is not good for me, maybe for you also. So here I'm done. You see, I made it in time.
You were even 30 seconds early, so we have time for several questions.
Peter.
Yeah, thank you. So one could argue that besides soundness and completeness, another important property of a logic is how natural it is to apply it, right? How naturally it captures the reasoning principles. So how applicable is a logic that you construct this way?
Yes, so this is essentially the question, why completeness? And completeness is very important because it's not understood. I don't know why. That it takes the system, you are odd if you are 0, or some even if you are 0, or even plus 2. Now, I can prove 6 is even. But I can also prove 5 is not even. I say, to prove 5, you have to prove 3. To prove 3, you have to prove 1. And 1 you cannot because there is no axiom. And so if you have OR logic, you can do the same. This is not false because I cannot do the proof. And this is not true. But if it's incomplete, you cannot do that. So you lose some power when you have an incomplete logic.
Do we have any other questions?
Yeah, the way I see it, the problem with completeness is that when you're trying to do relational proofs, it's actually not too hard to get completeness if you can be relatively complete by reducing your relational reasoning to unary reasoning. But that's not the proof you want to write. There are other proofs that are possible if you have other reasoning principles that are inherently relational that are not captured by being complete or not, because they're just additional rules that you can add that unlock different proofs that you cannot do with a complete logic that only has a reduction to unary reasoning.
If you are incomplete, additional rule may not be enough to get completeness.
Yeah, but you have more proofs, and maybe some of these proofs are easier to do than one.
Yes. So, but I have abstraction to do easier.
Right.
You see, my answer to easier is do some abstraction. It will be easier.
So we have time for one last question while the next speaker sets up. Is there any?
Can I see the last slide before the conclusion?
The last slide before the conclusion was, I don't remember what. And anyway, you cannot because she has to.
Okay.
So
there
can you
was
ask
an
your
inclusion
question anyway?
rather than an equality. And so what I want to ask if this affects the completeness of the corresponding hyperlogic or not. There was an inclusion, not an equality.
Yes. So this, you get an equality if you consider an abstraction of the hyper properties so that this abstraction will give you the equality. So you really complete in sense that the proof method of Dardinier and Müller will always be sound. And if your property is in this class that is closed by the abstraction, it will be complete, which is a nice result and easier.
So on those words, let's thank the speaker again.
Yeah.
Yeah.
Oh, not on metal.
We'll have to write.
Not on metal. Do it on your under the black stuff that you have below. Yes.
Not working on it.
J'avais des questions, mais pour après.
Is this okay?
Is it working? Perfect. So our next speaker, Lena Ferst, is going to tell us about many Hyperlogic logics.
Exactly. Yes, hi everyone. I'm Lena. I'm presenting joint work with Benjamin Kaminski at Saarland University on and what we want to do is we want to build a taxonomy of program logics. And when I say program logics, I mean, for example, Hall logic or incorrectness logic, which is also reverse Hall logic. Then Lisbon logic has been mentioned in literature recently. Just to name a few, there are many, many, many more. So the goal of this talk basically will be to bring some structure into this picture. So what we can observe first is that many of these are actually equivalent. But there are more relations between them that we're going to try to structurally examine. So, as I said, the objective, we'll try to build a taxonomy, and the frameworks that we're going to use are predicate transformers, mainly, and we're also going to take a quick look at Kleene algebra, or a variant of Kleene algebra. But I'm going to start with predicate transformers. In particular with the weakest precondition transformer, which takes as input some non-deterministic program P and some set of final states, so the post-condition here in blue C, and computes some set of initial states. Now there are different variants of weakest precondition transformers, different sets of initial states. So let's first take a look at what kind of initial states are there, or what can happen in an initial state. For example, computation can terminate in the post-condition, or it can terminate outside of the post-condition. Then we have non-deterministic choices, so it can also be that the computation either diverges, which is the spiral thing, or terminates in the post-condition, and this black box that you're seeing represents a non-deterministic choice in the program. And of course, the same can happen outside of the post-condition, and it can also be that computation terminates in C or outside of C, and of course it can also be the case that computation from an initial state always diverges. But that's it. So this gives us 7 classes of initial states, so to speak. And the different weakest variants contain different parts of, so to speak. So the first one that we're going to look at is the demonic weakest pre-transformer, which only contains this first class. So this requires all paths that are starting in this set of states to terminate in the post-condition. The angelic weakest pre-transformer only requires the existence of a path to the post-condition. So when I say angelic, demonic, you can think of there exists a path versus something has to hold for all paths. And well, we want to build program logics, right? So let's take a look at how we do this. And it's quite simple, actually. We just take a precondition, B, and require it to be included, for example, in the demonic weakest precondition, which gives us total correctness Hall logic. And if we do the same for the angelic weakest pre, this gives us Lisbon logic. Yeah, okay. Then there are also liberal variants of these transformers. And liberal basically means that they allow divergence. So for example, the demonic weakest liberal pre does not require computation to terminate, but if it does, it has to do so in the postcondition. And the angelic weakest liberal pre only requires the existence of either a diverging path or a path terminating in the postcondition. And well, we can add them here. If we under-approximate the demonic weakest liberal pre, we get partial correctness Hall logic. And for the angelic variant, we get some angelic variant of partial correctness. And yeah, let's take one final look at this picture here, because what we can see quite nicely is that there is a relation between these transformers, because you see the demonic weakest pre, the bottom row, is contained in these two transformers in the middle. And these are incomparable, but they are in turn contained in the angelic weakest liberal pre. And this directly translates to an order of implication between these logics that we've defined using the transformers. Yeah, so then there is this quite well-known equivalence between weakest pre and strongest post, because we can express partial correctness Hall logic using weakest pre transformers, but also using so-called strongest post transformers. So we're now going to take a closer look at those. So here's the picture that we had before. The weakest pre are backward transformers. They are starting with some initial states and computing, starting with final states, computing initial states. And now we're going to do the opposite. So we're going to start with initial states, compute some set of final states. So the direction of this program is now from bottom to top. Okay, and now what do these arrows mean in this case? Well, the first one, the one on the left, is just a final, or, yeah, represents a final state that is just reachable from the precondition B and from the precondition only. A bit more interesting, this diverging, or what was a diverging path. Well, what is a diverging path? It's basically an execution started in an initial state that is leading to nowhere. So the dual thing is kind of a final state where execution is coming from nowhere. So there's no initial state that can reach this final state. So this final state is unreachable. And to distinguish this, we're going to use these arrows coming from nowhere to visualize unreachability. Then we had these non-deterministic choices, these boxes, which were, well, representing like a path started in an initial state that branches into computation paths leading to different final states. But now these are just two computations that are, yeah, it's like a confluence of paths, which is not necessarily caused by a non-deterministic choice in the program, right? This can simply be caused by a statement which is not reversible. So I'm going to remove this box because there's not necessarily a non-deterministic choice present here. Okay, and now take a look at this second arrow. I said divergence is dual to unreachability. So what this would be is like a final state that is both unreachable and also reachable from the precondition, which in the setting of program analysis, this does not make any sense, right? And the same actually holds for all of these paths where we have a branching of divergence. So we can actually just remove them here from the picture because they do not exist. And this leaves us with only 4 different classes of final states, so to speak. And we're going to use them now to build strongest postcondition transformers. So this is the direction of this picture is reversed again. So we have initial states on top and the final states on bottom. And we have these 4 classes that we've just seen. And now we're going to define the strongest post variants. And we're going to start with a new one, which is the demonic strongest post transformer. The standard strongest post transformer is an angelic one. Why angelic? Well, the angelic strongest post contains all states that are reachable from the precondition B. Or in other words, there exists a path coming from the precondition. The the demonic strongest post requires that all paths were coming from the precondition. And maybe you remember this is very similar to the weakest pre case, just now these differentiation is not caused by non-deterministic choices, but by irreversible statements. And let's take a look at our picture. So we've had an over-approximation of the angelic strongest post already. If we under-approximate this, we get incorrectness logic. If we under-approximate the demonic strongest post, we get some demonic variant of incorrectness, which requires kind of exclusive reachability from the precondition. And now, as for the weakest pre case, we also have liberal variants of transformers, but now liberality in the weakest pre case meant divergence. Now it means unreachability. So these liberal transformers actually will only contain this third class, or additionally contain this third class of final states. So here's the demonic strongest liberal post, and here's the angelic strongest liberal post, which is also a new transformer. And yes, if we add them here, we get partial incorrectness for the demonic liberal variant and angelic partial incorrectness, yes, for this angelic liberal variant. And this means basically we do not require reachability, but if a final state is reachable, then it must be reachable from the precondition. Okay, then let's take one final look at this picture, because we can see here we have actually the same order of transformers that we had for the weakest pre cases, which again to these implications here. I said that the goal, well, our goal was to build kind of an exhaustive taxonomy. So we have now an over-approximation of a transformer here. So we can also over-approximate other transformers, right? For example, the angelic weakest pre. But it turns out this is actually, if we negate these conditions B and C, this is actually equivalent to partial correctness Hall logic. So these are kind of contrapositive to each other. And we use these green dotted arrows to symbolize contrapositivity. So you can read this as an equivalence if we negate the conditions. And now we can all other transformers. But it turns out they are actually all contrapositive to some logic that we've already seen. And we also have these implications between them. And we can do the same for the strongest post transformers. But they are, we also have these implications. And they are also all contrapositive to some logic that we've already named or seen. Yeah. And now there's only one thing missing, which is this equivalence here, which is not so surprising because we had this equivalence, or this equivalence here and these two contrapositive relations. And we've also shown in the paper that these are the only two Galois connect equivalences in this paper, in the taxonomy, sorry. Okay, so now if we're looking at this picture, this looks very symmetric, right? We have this backward analysis part here and the forward analysis part here, and they look completely symmetric. But I've just said a few minutes ago that we have this asymmetry between forward and backward analysis because this branching divergence cannot exist in the forward case. So the question kind of is, where is it? Why do I not see this here? And to answer this, we're going to take a look at Kleene algebra. And I don't have time to go much into detail. I'll just give a very brief intuition on how we can use Kleene algebraic equations to express program properties. So think of a program as a relation of input and output states. So here's a program P. We can add a second program Q and compose those, which is just composition of the underlying relations. Then we have tests, which are subsets of the identity relation and represent, in this case, a precondition, so sets of states. We can also compose them, and we couldn't do the same for a postcondition. And now the term BPQC contains the pairs 2, 2, and 3, 2. And now the clue with Kleene algebra with top-end tests is that we have this top element, which is the universal relation. And if we append this to the term, this actually acts as a selector of the domain or the codomain of these terms, because we now get a relation that relates all initial states to this codomain of the previous relation that we had, which is something that we need to express incorrectness, for example. Okay, and now program properties are just equations over these terms. For example, here's an equation for partial correctness. And there is this relative recent result of an equation for incorrectness logic. We were also able to find one for partial incorrectness. And now, total correctness Hall logic is known to be inexpressible in linear algebra. But we were able to find an equation for Lisbon logic, which is kind of cool because you see that these, from a transformer perspective, Lisbon logic and total correctness Hall logic are actually very related. So we were a bit surprised by this actually, but it was possible and we found an equation. And now if you look at these equations, they are syntactically very similar, right? And there are of course more equations that fit this pattern. For example, this one here or this one. The one on the bottom turned out to be equivalent to this new logic, angelic partial incorrectness, which is kind of cool because it seems that linear algebra in some sense agrees that this is a sensible logic to add to this taxonomy. And I want to spend a quick slide on the top one because what this means is that all computation that is started in this set of initial states B, either there exists a path reaching the postcondition or all paths must diverge. So this is kind of a mixture of this angelic demonic stuff that I've been talking about, right? And there's not a single transformer that captures this, but we can capture it using the union of two. And I won't have time to show you this now, but this actually fits quite nicely into this taxonomy. And there's also kind of funny relation to outcome logic. So take a look into the paper if you're interested. And what I am going to show you now, though, is this taxonomy that we had before. And now here are the logics that are expressible in linear algebra. And now you see there's this gap up here, which is an asymmetry in this picture, which is kind of what we wanted, right? So this is very nice. Yeah, in the paper we also looked at like conditions that we can discharge so that logics collapse. For example, if the program terminates, we know that total correctness and partial correctness are equivalent. And this actually holds for several of these logics. So there are these axes along which program logics collapse under different assumptions. So we've looked at this here, for example, and also this appeared in the paper. Yeah, so this is quite cool because you see what logics you can use to prove other logics, on which tools you can combine potentially. And now there are many open questions still. For example, we have these equations for linear algebra with these equivalences between them. And it would be cool to see if we can find some kind of syntactic recipe to get from one equation to the other that represents this Galois connection. Other open questions include like variants of linear algebra because we've only been looking at a very specific variant. Then another point that I want to mention is the names of these logics. I'd really like to find names for all of these logics that represent like all properties, all kind of properties that I can express. And yeah, there are many more open questions. I think I'm out of time, so I'm going to refer you to the paper for more illustrations and even larger taxonomy, and also a comparison to existing taxonomies. For example, the abstract interpretation one. So, yeah, thank you.
Thank you. Very beautiful work. I guess I'm curious if you can go to the slide where the linear algebra breaks the symmetry. It's kind of puzzling because linear algebra, there is no notion of backward or forward, right? It's completely symmetric. It's just a relation. So how can that break the symmetry between forward and backward reasoning?
Yeah, interesting question. It's actually the reason for this gap up here. For the gap that you see, is actually this asymmetry of forward and backward analysis, because in program executions, like you cannot have this branching you can have a branching of divergence which cannot be captured by linear algebra. So while linear algebra is symmetric in some sense, like the underlying relation is not, because program execution is not symmetric, if that makes sense.
Yes. Maybe a follow-up question. If you would add, linear algebra has the star that does forward iteration. If you would have a star for backward iteration, you would express those two?
I'm not sure because we're using this relational abstraction, maybe. I'd have to think about this in more detail, but it's an interesting thought. Thank you.
Hi, sorry, just to drone on about the connection to Kleene algebra. I think, so that connection, right, between these subset relations that you have and the equations, it goes a little bit further to the point where you can prove these equations, like you can relate these equations to rules of inference in propositional Hoare logic. Have you explored that connection as well? Like, are there rules of inference that you can validate using their Kleene algebra counterparts?
I have not looked into that, but it would definitely be interesting, in particular for these logics here, for these strongest post variants, because they are kind of new, and I wouldn't know how this looks in Hoare logics there.
Let's chat about that.
Yeah, let's do that.
We have time for one more question.
Could you get something about having, rather than pre and post condition, which are concrete pre and post condition, abstract post condition, and abstract precondition, so ranging in some abstraction? Does something of this taxonomy should be still there? I know it's very vague question, but maybe you have some idea.
I'm not sure how you would define abstractions of these pre and post conditions. I mean, there's this work on like a weakest hyper calculus. Maybe you could express something like this in here, and I suppose for the weakest pre-variance, at least it should hold. There are some problems with the strongest post in these in this area, but I'm not entirely sure. Maybe next year I'll give a talk about this in the hyper setting.
So let's thank the speaker again. And this concludes the session. So thanks for coming, and let's have a coffee break.
Okay, hi everyone. Welcome to the theory session, which is the penultimate session here at POPL. And I think we can just go ahead and get started. So our first talk today will be by Vikram Chowdhury, who's going to tell us about the duality of lambda abstraction.
Hello. Hi, I'm Vikraman from the University of Bologna. I'll tell you some nice ideas about how the lambda calculus can be dualized. I personally think it's very beautiful. I'll try to convince you in 17 minutes to look at my paper. So I'll start with a very simple puzzle. We've been thinking about the lambda calculus for a long time. It's a theory of higher order functions. So if you take your favorite typed functional programming language, you can implement curry and uncurry, right? So what curry does is you have products on the left, and it gives you a higher order function on the right, and you can go forwards or backwards. But can you dualize currying? Okay. So what does it mean to dualize currying? We know products are dual to sums, so let's put sums on the right. And now I want something on the left which is dual to functions. Okay. So what's a dual to functions? And can you actually get it in a functional programming language? Okay. So it's an interesting puzzle, but the answer is very boring because if you have both currying and co-currying, your language becomes degenerate, which means you can't compute anything with it. So let me give you a simple argument or a sketch of the argument of how this works. So if you have the empty type, the product type, the function, and the co-function, you have one unique way of going from 0 times a to 0, okay, by currying. And if you want to go the other way, there is one unique way of going from 0 to 0 times a, because going into a product means going into both sides of the product. And from this, you can show that 0 times a is isomorphic to 0. Dually, if you have co-currying, there's only one function from 1 to a plus 1, and a plus 1 to 1. So dually, you just get a plus 1 is isomorphic to 1. Okay. Now, if a plus 1 is a times 0 equals 0 is completely fine. That matches our intuition with the empty type. But if a plus 1 is equal to 1, then you'd have 1 plus 1 equals 1, which means you can't have Booleans because you want true and false to be two different programs, right? So this is a technical argument in category theory, which is known as Joyal's lemma. If you have both a Cartesian closed structure and a co-Cartesian co-closed structure on the same category, it degenerates to a preorder, or in particular, it becomes a Boolean algebra, okay? So why am I telling you about this puzzle? Because in 2022, I was reading Girard's book about classical linear logic and why Girard was thinking about all these things. And one of the main arguments about classical linear logic is you can't have duals to functions. So Girard argues that actually you should start from linear logic, where all the connectives are linear, and find a way to dualize everything. So if you have classical linear logic, you have complete duality with tensors and cotensors, and every type has a dual. Okay, in this talk, I'm going to show you a language which has both currying and co-currying, but it's not classical linear logic. It's almost like classical linear logic, but the only restriction that I'm going to put on the language is that it's call by value, okay? And this is not just a simple solution to the puzzle, but when you do it like this, you realize that actually there is a deep insight between co-currying and classical logic and control operators like call CC, okay? And why is this interesting to a programming language audience is because if you do it like this, you get a very nice programming abstraction. I think it's nice, I'll tell you about it. So let me tell you what the trick is. So you want co-curry to take C to a plus b, but instead of c to a plus b, I'm going to double negate the sum, okay? So I'll write c to a plus b to r. When you do this, you can look at the continuation for the sum, which is a plus b to r. You split it into two continuations. One takes a continuation a to r, and the other is b to r. Then you apply currying and move the left continuation to the left and the right continuation to the right, and put the b back inside a double negation, okay? So that's the whole trick, and this is the only thing you have to remember to understand the rest of the paper. But if you actually write down this isomorphism in your programming language, like ML or Haskell, you can do a bit of hacking with two continuations for the left and the right. And this is what the program looks like for co-curry and co-uncurry. Okay, so this is a very nice program, but I want to abstract away from it, okay? So the first thing I want to write is these double negations are, in fact, a continuation monad or the double negation monad. So I write Ka to be A to R. And the dual to the function type is going to have a value for B and a continuation for A. And then you look at the type signatures for co-curry and co-uncurry, and there's a K in the codomain of these functions. Okay, and you can do the same thing for curry where you insert a K into the codomain for the function. So the whole trick is you have curry, uncurry, co-curry, and co-uncurry as long as you insert some double negations in the right places. Okay. Okay. So this is a nice trick, but I'm a category theorist. I like to understand things from a deeper perspective. So I won't tell you the full details, but you can read the paper to find out what exactly it is. So the trick is really about Kleisli categories. So the continuation monad is a strong monad, and it has a Kleisli category. And when you have a strong monad, you can have a nice, well-behaved notion of weak exponentials. And the Kleisli category for the continuation monad has some additional structure, which is really interesting. It allows you to construct left adjoints to sums, okay? And the whole premise of the paper is to take these two adjunctions and understand the duality of lambda abstraction. Okay, I will not explain what the trick is here, but we can talk more about it offline. I can tell you lots of interesting facts about negations and adjunctions, okay? So I'll introduce this calculus, which I called the lambda bar calculus. So it has lambdas and co-lambdas. So the first two rules are the usual lambda calculus rules, okay? And the second rules, the second row has two other rules which are dual to lambda introduction and lambda elimination. So what the difference is between the rules is that lambda binds a value and lambda bar binds a co-value. Lambda application eliminates functions, and co-lambda co-application eliminates co-functions. Okay, now you might be a bit surprised, why is there a sum type here? Okay, it's an A plus B. Okay, so let's try to give a logical reading of these typing rules. So, so the lambda bar introduction rule assumes something which is of type A dual, which means A is not true, and it tries to prove B, assuming A is not true. So this is a weird kind of sum where you're not proving directly B, but in a weaker context where you assume A is not true, okay? So this is different from an intuitionistic sum because you don't know whether A is true or B is true because there is an additional assumption like A must not be true, right? So when you look at the type of the co-lambda, lambda bar x dot E, it has the type A plus B, but this type A plus B behaves like a classical sum. Okay, and the dual to this is the application rule, the co-application rule. So if you have A plus B, and you know A is not true because you can prove A dual, then you cancel out the A and you get a B. Okay, so this is how the typing rules work. And I'll show you some interesting programs you can write using these two typing rules, okay? So when you have functions, you have lambda x dot x, which is the identity function. When you have co-functions, you can write lambda bar x dot x. And the type of this is A plus A dual, okay? When you have functions, you can evaluate them. When you have co-functions, you can co-evaluate them. When you have functions, you can do uneval, and with co-functions, you can do co-uneval. You can compose functions, you can co-compose functions. There's a very nice algebra to these co-functions. And you notice that I'm writing minus because when you look at the typing rules, it behaves like a minus because B plus A minus B gives you A. Okay? So this minus is the dual to the formal dual to the function type. It's like a subtraction operation. Okay? And with these typing rules, you can also make values and co-values interact. Okay? So we've already seen the excluded middle, which is lambda bar x dot x. If you have A and A dual, that's like A minus A. And then you can lift the A to the left and co-apply an A dual, which allows you to prove anything of type B. If you know about call CC in SML, so A dual to A, it takes an argument f of type A dual to A and gives you an A. So you can derive call CC by writing lambda bar x dot f of x, which gives you a plus a. And then you collapse both sides of the sum by doing a pattern match using case. Okay? If you want to prove Peirce's law, it's the same kind of thing. You always have to collapse both sides of the sum. And you can show that you can get all the axioms of a Boolean algebra and all the classical control operators using just these typing rules. Okay? Okay, and now how do you run these programs? So the lambda bar is dual to lambda. So lambdas have substitution, so you get beta eta rules. Lambda bar also has substitution, you get beta eta rules. Because the language is called by value, I have to restrict the substitution to values. But the lambda bar operator has a strong eta rule, which is lambda bar x dot e co-applied to x. Okay, so this is the binding. These are the equations for binding. But there's also something more in this calculus, which is how the intuitionistic sums interact with classical sums. So because both of them have the same sum type, so you see there are three different ways to introduce sums, right? You can either introduce them intuitionistically using left and right, or you can use a lambda bar, which is the co-function. And you can eliminate sums either using case or by co-applying. Okay, so for every pair of interactions, there is a control effect. Okay, so what happens if you introduce an intuitionistic value and then try to eliminate using a co-application? So let me give you two equations. So lambda bar k of type A dual, it's assuming A is not true, right? And then inside the body of the co-function, you say actually I know that B is true. So I can just do in right. And then, just forget the lambda bar, and it just goes back to in right outside. Okay, and what if you do the other thing? So you assume A bar is not true, but inside the body of your co-function, you realize actually A is true. And then it's going to jump out and backtrack to the outside. And during that jumping effect, it's going to forget the evaluation context. Okay. And then there's another way of interaction. So if you introduce something classically and try to, so you have a lambda bar x dot v, where v is a value, and then you're trying to observe it with a case. And then the case is going to start executing the right-hand side of the branch and push it to the body of the co-lambda. Okay, so these are the three equations that are very important. And then there are other eta laws that you have to make the language complete. So let me try to give you a very classic example of a program which was in the original call CC papers. So you're trying to multiply a bunch of numbers in a list. You write your simple ML program, but then there's a 0 in the middle of the list. So you do a bunch of vacuous multiplications with 0. So it's a very long list. It takes a long time, right? Okay. Now you can short circuit this computation and just say in your pattern match that if it's a 0, just don't do multiplication anymore. But that's not good enough, right? Because it's still going to do multiplication on the right of the 0. Okay, now if you have intuitionistic sums, you can actually say, okay, it's an exception, right? So if I have a 0, I'm going to move to the left. So you say int plus int. But if it's a 0, you do in left 0. And if it's otherwise, you just keep mapping things on the right. Okay, and I'm adding a trace function here. The trace is right to left in the style of SML. So it's going to evaluate x and then print the statement. Okay. So if you call this multiplication function now with 0, 3, 4, it's not going to perform any multiplications, but at every step, the evaluation context of the print is going to be executed. So it's going to print at 2, at 1. Okay. Now, these are intuitionistic sums, but now you can rewrite them using classical sums. So it's the same program. Now it has a sum type, but I'm going to do a co-function. And it's the same program, except when you look at the 0, you do the co-application on the left. So in left 0, co-applied to k. Okay, and when it reaches the 0, it's actually going to jump out by discarding the print evaluation context, and you don't see any trace. So this is how classical sums are, give you more expressive power than intuitionistic sums. So let me just, so there's a lot more in the paper. I'll just summarize a few different things. So these CPS translations, there are different kinds of them. but there's a very nice categorical structure behind them using these duals to function types. And in the paper, this is all explored in more detail. And one nice thing I like about this point of view is you can take all the classical results about the lambda calculus and dualize them very formally. So you can dualize functional completeness, you can dualize arrow languages. And this whole co-exponentials and the lambda bar gives you the Curry-Howard correspondence for classical logic. And you can actually give an axiomatization of all the control effects using these classical sums rather than the empty type. Okay, so if you go through the paper, I explain how you can recover all the original axiomatizations of call CC or call by value lambda mu. Okay, and I also enjoy programming with co-currying and co-lambdas. So if you look at the types of co-lambdas, it's like a generalized call CC, which doesn't collapse both sides of the sum. Okay, and they are equally expressive, so you can derive call CC using co-lambdas. You can use call CC to derive co-lambdas and the other way. But call CC kind of captures the whole stack, but co-lambdas capture part of the stack. And I have written many programs using co-lambdas, and I really like them when I do backtracking, when you have two continuations. So there's a SAT solver, there's tree search, and I've also implemented a library for effect handlers. You can also play around with this calculus using my interpreter, which is on my on the artifact, and you can implement them in various languages you like. So just to conclude, what's the point of all this? I think continuations are a very well-studied topic, and there's obviously a lot of literature on this. All I'm saying here is a different perspective on continuations and the logical foundations using classical logic. And I really like thinking about classical logic as a computational effect on top of intuitionistic logic, because it changes the way sums work. And I like this point of view of backtracking that classical logic gives you. So I'm happy to tell you more offline about co-lambdas, but if you're teaching your students continuations, maybe you'll tell them about co-lambdas, or if you are programming, maybe you'll think about co-lambdas instead of call CC. There's a lot more to understand about these things. I think this point of view of classical sums and their proof theory, and yeah, I'm thinking about a bunch of these things. Yeah, all right, I'll stop here. Yeah.
All right, so we have time for a few questions. So does anyone want to start? Raise your hands if you would. Can you get to Bob?
Thanks for a great talk. I just had a slight question. I didn't quite see where you got forced to call by value. I know that you must.
Yes.
I don't disagree with that.
I
didn't see the spot.
I didn't show all the equations, but here's the lambdas.
It as call by value, but I was wondering the point at which you feel forced to do that.
Yes. I mean, semantically, you mean? You mean semantically, why is it called?
Yeah, like where somewhere.
Yes. It's just because.
Opening example must come into play.
Yes. So there's this thing where I'm working in a Kleisli adjunction, and the exponentials are really called by value exponentials because there's a monad hidden inside. Yes.
Okay,
Yes.
Well, and then I think the other thing that's fun to do, which you could do, is you write down excluded middle.
Yes.
And then you'll say that it's a computation and not a value.
Yes.
Whereas all the intuitionistically valid things come down to value.
Yes.
Okay, we have time for another question. Yeah, right over here.
We know classically how to convert lambda abstractions into combinators.
Yes.
Have you got a combinatory account of co-lambdas?
I don't know. I don't know of such a thing. I'm thinking about it. Yes. Yes.
Okay, let's all thank Vickerman and could the next speaker come up. Okay, so our next speaker is Naoki Kabuyashi, who really needs no introduction in this community, and he's going to tell us about decidable and undecidable extensions of the simply typed lambda calculus.
Okay, thanks for the introduction. So this work is concerned about the reachability problem for extensions of the simply typed lambda calculus with recursion. In the paper in the proceedings, we first give simple proofs of undecidability of the reachability problem for Boolean PCF with each of these extensions. And in the second part, we give a decidable fragment of Boolean PCF with references by using a kind of ownership types. So first, let me explain why we are interested in the reachability problem for extensions of the simply typed lambda calculus. So it is known that for pure Boolean PCF, that is a simply typed lambda calculus with recursion and Booleans, the reachability problem is decidable. And that has been used as a foundation of fully automated verification tools for function language like Mochi, which we have developed about 10 years ago. So this figure shows how Mochi works internally. So given an OCaml program as an input, we first apply predictor abstraction to get a high-order Boolean program. And then we invoke a high-order model checker to decide whether this abstract program is safe or not. And if it is safe, we can conclude that the source program is also safe. And otherwise, we get an error path of the abstract program. And if the source program has a corresponding error path, then we can conclude that the source program is buggy. And otherwise, we get a new predicate to refine the predicate abstraction further. And we repeat this cycle until we eventually can prove that the program is safe or unsafe. And obviously, this relies on the decidability of the reachability problem for these high-order Boolean programs. And this works fine for pure functional programs. But if programs have some impure features like references and high-order exceptions, then this will break down. And that is because in that case, this Boolean program also has a corresponding impure features. And then high-order model checking problem is undecidable, unfortunately. So to convince you that this is a real issue, let me show you a snapshot of the web interface of our tool Mochi. So here is a sample OCaml program, which asserts a property about McCarthy's 91 function. And for this kind of pure functional program, Mochi works fine. And indeed, for this program, Mochi can verify it in just a few seconds. And Mochi now supports a fairly large subset of OCaml, including high-order functions, recursion, algebraic data types, and exceptions. But when it comes to programs with references, it is extremely imprecise, although syntactically it does support references. So here is a program, simple program, that just creates a reference cell X and asserts that its content is 0. So this assertion should obviously succeed. But unfortunately, Mochi cannot prove that. And that is because the underlying higher-order model checker does not accept programs with references, so that Mochi first replaces every reference of integer reference with a non-deterministic integer value. And that's why Mochi fails to prove this. So addressing this kind of issue has been a major motivation of this work. And in the rest of this work, in the rest of this talk, I'll completely skip the first part of the paper and focus on the decidable fragment of Boolean PCF with references. So we consider this call by value Boolean PCF with references. And I omit the type system, but we assume that programs are simply typed. Okay. So the black part is ordinary function language with recursion and Booleans. and fail is a special command that aborts the program. Okay? And red part shows ordinary ML-style reference primitives. And then for this language, I believe that it is the reachability problem is undecidable. And I believe this is a classical result, but actually I'm not completely sure whether this is an appropriate reference because they consider call by name language. But anyway, our paper gives a simple proof for the call by value case. And please note here that without references, the reachability problem is decidable. And that is an immediate corollary of the decidability of higher order model checking. And we indeed now have a reasonably good higher order model checker that decides this problem, although the worst case complexity is hyper-exponential. Okay. So based on this undecidability result, we wanted to find a decidable fragment by using a type system. So the main idea was to restrict Boolean PCF with references by using a sort of linear type system to ensure that no live alias exists for references as well as for reference capturing function closures. And based on that restriction, we can construct a type-based translation from the restricted fragment to Boolean PCF without references. And that is achieved by what we call local store passing translation. That is a variant of standard store passing style translation, but we only pass around local store that is used in each function. So let me explain a little more details about that. So the first idea is to introduce ownership control for references so that no live alias exists for a mutable reference. So here, this program first creates a reference cell X and creates an alias Y of X and use X and Y afterwards. Okay. So for this program, both X and Y are live at this point, and we forbid this kind of aliasing situation. And in contrast, this is fine because although alias Y is created here, only Y is used afterwards. So in this case, only Y is live at this point. Okay? And the latter program can be converted to a reference-free program like this. So here, we just replace a reference cell with its contents, and we just remove the reference operations and replace update operation with let binding. Okay? So actually, this kind of idea has been already used in our recent work on automated verification of first-order programs with references. And this work is a sort of extension to deal with high-order functions, possibly capturing references. Okay? So to deal with functions capturing references, we also impose a linear ownership principle for reference capturing closures. So this program first creates a reference cell X, and that is captured by function f. Okay? And alias G of f is created, and G and f are used afterwards. So at this point, both f and G are live, and we forbid this kind of situation where multiple alias exists for reference capturing closures. Okay. And in contrast, this is okay because at this point, only G is live. Okay. And the latter program can be converted to this reference-free program. So as before, reference cell is replaced with its contents. And the function f is represented as a pair consisting of its local store x, which is captured by the function f in the source program, and a code in store passing style. But only the local store x is passed around here. And in calling function g, we first extract the local store of g, and then invoke the code part of g, like this. So this also has a flavor of closure conversion. And also, we need to ensure that so this is reference-free program, and we also need to ensure that this is simply typed. So to ensure that we impose additional restriction, and that is to impose a static bound on the number of captured references. And that is ensured by using a type system. So here, this program creates references x and y, and creates a function f that captures reference x. Okay? And then this f is given this kind of type. And here, 1 over the arrow expresses the fact that one reference is captured by this function f. Okay? And this next function g captures reference cell y, as well as x indirectly through this function f. Okay? So that this g is given this type. So now this 2 indicates that 2 references, x and y, are captured by g, okay? Or owned by g. And then based on that information, we can convert this to reference-free, well-typed program, simply typed program. So here, as before, x and y are references x and y are replaced with their contents. And the function f is expressed as a pair consisting of the local store and coded in the store passing style. And f is given this simple type. Okay? So this part is a type of the local store. And g is also represented as a pair consisting of the local store, which is the values of x and y, and the code in the store passing style. Okay, then again, g is also simply typed like this. Okay. So based on these ideas, we have formalized a type-based translation to remove references, and prove that the result of translation is a well-typed term of Boolean PCF, and reachability property is preserved by the translation. Okay. So as a corollary, we get that for programs well-typed in our type system, the reachability problem is decidable. Okay, so, and actually the type system as formalized in our paper is quite restrictive. So in the basic type system in the paper, if once a reference is captured by a function, that reference cannot be used outside of the function, even if the function becomes garbage. So this kind of program is disallowed. But actually, we can allow this by introducing more flexible ownership control by using Rust style and or consort style ownership types. And then we can apply the prophecy-based translation of Rust Holm, which is also our previous work. Then we get a reference-free program. Okay, so let me briefly discuss applications to automated verification. So far, I have considered programs with only Booleans, but our translation actually works in the presence of other base types, such as. So we can, so given programs with references, we can first apply our transformation to get programs without references, and then use off-the-shelf verification tool for pure functional programs. Okay. So to check the effectiveness of this kind of approach, we have manually translated several tricky programs and fed that to Mochi. And then we could distinguish between this kind of these kinds of programs with a subtle difference. So here, in the first program, reference cell X is first created, and that is incremented each time F is called. And in the second program, X is created each time F is called. And we can correctly distinguish between these two programs in our approach. Okay. So now let me conclude. So I have completely skipped in this talk, but in the paper, we also give simple proofs of undesirability of various extensions of Boolean PCF. And we constructed a decidable fragment of Boolean PCF by using a kind of type system. And in future work, we plan to extend this and formalize and implement it more flexible control via lifetime and also fractional ownerships. And we are also thinking about redesigning a functional language with last style ownership types. And then our translation would work better. And also here we focused on references, but our idea may be applicable to also some of the other effects, such as resource usage. So we plan to investigate generalization of that. So that's all, and thank you for your attention.
Okay, so we have plenty of time for questions. So who'd like to be first? Yes.
Thank you. So in Mochi, you showed at first an example where you have a reference and you over-approximate the reference by just non-deterministic value. So now that you have this translation, do you treat programs that are well-typed exactly? And if they're not well-typed, you're still doing that non-deterministic over-approximation? Or can you maybe translate a part of a program and only the part that is not eliminatable is treated as an over-approximation?
Okay. Yeah, so basically in general, it is hard to type all the reasonable function programs in our type system. So what we have in mind is that for differences conforming to our linear ownership principle, then we can apply our translation to remove them. And for the other references, we just leave them there and pass them to existing tool. So for differences that do not conform to linear ownership principle, the analysis remains imprecise.
So you will distinguish precise references and imprecise. Okay, cool. Thank you.
All right, do we have any other questions? Okay, I have a question of my own. So my understanding is that higher order model checking works better for linearly typed programs.
Yes. Yeah.
So have you thought about, like sort of Mochi for Rust? Like, would you be able to get better scaling for a language that is sort of natively substructural?
Well, so that is a different issue than differences. So actually, yeah, we could possibly optimize the current high order model checker, but actually the current high order model checker sort of already takes into account, can take advantage of linearity without modifications.
Okay.
So we have not tested, but yeah.
Okay, thank you. So let's all thank our speaker again, and could the next speaker come up? Okay, so while she's setting up, I'll just introduce Adrian Lancelot, who's going to tell us about interaction equivalence.
Is the sound good? Okay, thank you. So I'm very happy to present this work today. I'm in my final year of PhD, and this is work done with my 2 PhD advisors, Beniamino Acatoli and Giulio Manzonetto, and also with a postdoc in our group, Gabriele Vanoni. So a central topic in the study of programming languages is program equivalence, and how do we check, how do we prove whether 2 programs are equivalent. So we'll focus on this talk in the untyped lambda calculus. And here, because of the syntactic nature of the lambda calculus, you can already build equivalences based just on the syntax and on identifying terms that are related because they have the same normal form, and possibly identifying them if they have the same infinite normal form. So this is a syntactic, a natural equivalence, but it is in general not enough. There are some programs that behave in the same way, but do not have exactly the same normal form, the same infinite normal form. So to deal with these, we have the notion of contextual equivalence that tells us when 2 programs are equivalent. So T and U are equivalent if if in every context they behave in the same way. And what I mean by behaving in the same way is that they reduce to an observable. So this notion of contextual equivalence really depends on what you want to observe. Usually in the lambda calculus, we consider a notion of reduction as an observable. And one of the most well-studied is head contextual equivalence, so where we set the observation to be having a head normal form, being in head normal form. And so this is because of the central concept of head reduction linked to solvability. So this head contextual equivalence is an equational theory. And what I mean by this are the 3 points: that it is an equivalence relation, that it is context closed, stable by context, and that it is also invariant, stable by beta equivalence. And so the first 2 points are really easy to see from the definition of contextual equivalence. The last point requires a bit more work. So if I move from this notion of a contextual equivalence where we only observe the result of a computation and try to also observe some things with the computation, I can, for example, observe the number of steps that it takes to compute. And so this is linked with the theory of improvement developed by Sands. And so here I will talk about the symmetric version, the definition of cost equivalence. And so cost equivalence is exactly this. T and U are cost equivalent if in every context they behave in the same way, meaning they give the same result and they give this result in the same amount of steps. So if we again go to the lambda calculus and we specify observation as head reduction, we will observe that 2 terms are head terminating in the same amount of steps. And so this is not an equational theory. It cannot be invariant by beta because beta will obviously change the number of head steps. So the starting point of our work is, can we mix both concepts? Can we have somehow a contextual equivalence, somehow a cost equivalence that is still an equational theory? And so our idea is to be able to the internal dynamic of a program, but only count the interaction of the program with the context. And so this is the idea behind interaction equivalence. But how do we know what are the internal, what are the external steps, what are the interaction steps? And so our first contribution is to propose a framework to be able to really differentiate between these internal and external steps. And so this is, we call this the checkers lambda calculus, and I will introduce it a bit later in the talk. So this interaction equivalence is really this idea that we want 2 programs to be equivalent if they make the same amount of calls, the same amount of communication steps with the context. It will be an equational theory, and we were heavily inspired by game semantics, and I think this is really reminiscent of the duality there behind, between context and programs. And this is also a bit related to how composition works in process calculi in the pi calculus and with label transition systems. And so we really want to count somehow the number of accesses, the number of resources that a program needs that are external to the program, so ignoring what's going on internally. So these contextual equivalences are really natural. They are really natural to define, and this is something that one could come up with easily. But these are really hard to check. There is this for all quantification on context. This basically means that you need to try your program for every possible input. So these are hard to check and hard to prove in practice. On the other end, there are equivalences that are very easy to check or easier to check, that are more intentional. So I gave, for example, here, Böhm tree equivalence, normal form by similarity, building the set of approximants of a program. But there are others. And so our second contribution is to be able to relate this black box principle, that is interaction equivalence, with actually an intentional equivalence, so Böhm tree equivalence. So this means that we will provide a proof method that is how to check that two terms are interaction equivalent. You build the Böhm trees, and then you compare the Böhm trees. This is still not decidable, because the Böhm trees are infinite, and building the Böhm tree is not even decidable, but it gives you a proof method, and then you can actually check what are interaction equivalent programs. So this is also backwards on the other way, answering an open question in the lambda calculus that was, what could be a contextual equivalence that matches exactly Böhm tree equivalence? So now I'll go a bit more in-depth and actually present to you the checkers lambda calculus. So the usual lambda calculus is made up of two constructors and variables. So we have variables, and then the abstractions and application. And so we move to the checkers lambda calculus by duplicating somehow the two constructors. So we color application and abstractions with a tag, so either black or white. We keep the variables unchanged. And so we have a black lambda and a white lambda, and a black application and a white application. So we need to make explicit the application to be able to differentiate between them. And so the intuition is that you want the context and the term to be separated colors so that you know who is what is the context, what is the program. So let's paint the context all in white and the program all in black. But of course, this is at the beginning of the computation, and then you will compute and everything will get mixed. So how do we compute in this calculus? We compute as usual with beta reduction, but because we have colors, we have actually 4 variants of beta reduction, depending on the color of the lambda and then the color of the application. So we have what we call silent steps, where these are somehow monochromatic redexes, where the color of the application matches the color of the lambda. So that means that this is the program computing on its own, or the context computing on its own. And then we can mix these colors and have interaction steps. So when we have that the color of the abstraction does not match the color of the application. And so, for example, the first of these rules is somehow the program, that's in black, asking for an argument from the context. And so, yeah, the result of all these steps is, as usual in beta reduction, we just do the capture-free substitution. So this is the calculus, and we want to know where are the interaction steps, where are the silent steps. But of course, this is a calculus, and counting interactions will depend on the reduction sequence. So I give you here an example where we have the duplicator, the black duplicator, applied to an interaction redex. And depending on how we do the computation, we will either first reduce the interaction redex and then do all silent step, or first duplicate the interaction redex, and that will mean that we'll have to do at least 2 interaction steps to get to the same result. So this calculus is confluent. We can always get the same result, but we will not preserve interaction steps for all the calculus. So that means that if we want to have a notion of interaction cost, we need to pick a reduction sequence. And so we pick the head reduction sequence, again, for all these, for the fact that it is a central topic and really linked with solvability. and we consider the head interaction stock. So head reduction is deterministic. There can only be one number of head interaction steps. And so this notation means that T terminates with the head reduction, so T, a colored term, terminates in the head reduction with K interaction steps. So the number K only counts interaction steps. And so now that I have this calculus that is able to see what are interaction steps, what are internal steps, I can build a contextual equivalence that is somehow quantitative in that it counts the interaction steps. So we have T and U. So this is in the checkers world. This is still colored terms or tag terms. T and U are quantitatively, contextually equivalent if in all colored contexts, they have the same behavior in that the head terminates with the same amount of head interaction steps. And so this is the contextual equivalence, but a lot of the time when we're working with equivalences or relation between programs, we also want to introduce a preorder so that we don't have to do every proof twice. And so we say that U simulates T, not if they have exactly the same behavior in all contexts, but if U can do at least as much as T. So that in all contexts, when T terminates with K interaction steps, U will also terminate with K interaction steps. But we do not specify what happens when T does not terminate in that context, in a context. So the key point is that because we have been able to characterize what are interaction steps, what are silent steps, we can only count interaction steps. So we pull this back into the usual lambda calculus by just introducing interaction equivalence as we paint the program black, and then we look at what is the equivalence class in the checkers world. And so here the program will be all black, but the context, I said that they were colored contexts, they can have both black and white constructor. So this is the definition of interaction equivalence. It is an equational theory. It's really easy to see that it's an equivalence relation. It's context closed. Colored contexts are stable by composition. Invariance, again, is a bit more complicated, just because it's not easy in the first case. It requires some rewriting theorems. And the key point is that, of course, if I paint my term black and I could reduce it without painting it, it will still be a silent step. If it's all black, I can only do silent steps. So I told you about this interaction equivalence, but what are actually inequivalent or equivalent terms for this interaction equivalence? So the big thing is that interaction equivalence is not stable by eta equivalence. So eta equivalence is just T is equivalent to lambda xt applied to x, where x is not a free variable of T. And so this is an example of terms that are not interaction equivalent. So we have the identity and an eta expansion of the identity here named 1. And so we have a separating context, C, that is an all-white context that just applies two variables. And this distinguishes 1 and the identity, because when we paint 1 all black and we put it in this context, and when we paint the identity all black and we put it in this context, we do not have the same behavior. They both terminate, they both reach a similar normal form, but not in the same amount of steps, not in the same amount of interaction steps. One will make 2 interaction steps, and the identity only 1. Somehow these are different normal forms, but this is just because we added colors. If there were no colors, these would be the same normal forms. So these terms are usually contextually equivalent. So this means that the interaction preorder or the interaction equivalence strictly refines its contextual counterpart. So we are between beta equivalence and contextual equivalence, contextual preorder. We can actually do better. We can characterize exactly the interaction preorder by the preorder induced by Böhm trees. And so I have no time to tell you about the technical details of this proof, but what's interesting is that we use really well-known techniques and standard techniques for the theory of the lambda calculus, namely intersection types, which we paint in black and white, and the Böhm technique adapted to interaction to the checkers lambda calculus. So when I told you about the definition of interaction preorder, maybe you would have expected something different, in that the interaction preorder just means that U simulates T, means that U can handle more cases than T, but when it handles the cases, it has the same amount of interaction. Whereas maybe you would have expected something along the lines of the interaction improvement, which says that U actually improves T. It can handle all the same cases, maybe more, but in the handled cases, it can actually do better. We could have that T in the context C makes K interaction steps, and U makes K prime that could be less than K. So this does not change the induced equivalence relation. We still have the same notion of interaction equivalence, but this is somehow about optimizing interaction steps. And so for this, we do not have a complete result yet, but we see that eta reducing terms may improve them because we are reducing the syntax of the term. But eta expanding them for sure will never improve a term. So as future work, we'd like to characterize exactly what is the interaction improvement. So we know that it's between the interaction preorder and contextual equivalence. And so because the interaction preorder is POPL'25 preorder and the contextual preorder is POPL'25 with eta equivalences added to it, we think that it can match the POPL'25 preorder up to eta reductions only. So to conclude, we've introduced the checkers lambda calculus, that is a new framework to be able to tell what is an interaction between programs. And then we can define interaction equivalence, which is a cost-sensitive equational theory. And it is the first contextual characterization of POPL'25 equivalence without using effects such as non-determinism in the context. And in our opinion, it is quite simple. So for future work, we'd like to work this out in call by value, call by need, maybe revisit some of Sen's results, and also in effectful extensions of this calculus. A big question is, we were inspired by game semantics. This looks a lot like game semantics, but we have no formal relationship with game semantics. Maybe there could also be a relation with process calculi. And also, what does exactly this head interaction cost represent? We have no idea. I put here the keyword communication complexity because it looks like distributed systems talking to one another. But we have no expert on this topic in the authors. Thank you for your attention.
All right, I think we have time for one or two questions. Does anyone want to ask a question?
So this might be a bit general question. So do you think that your result could improve practical decision of equivalence, of say POPL'25 equivalence, by some kind of co-inductive technique, for example?
Do you mean whether interaction equivalence could help in proving that things are POPL'25 equivalent?
Yeah, exactly.
No, I don't think so. Maybe it could help disprove things because it's usually easier to disprove contextual equivalence than for POPL'25 or this co-inductive definition. But POPL'25 preorder can be defined co-inductively, and you just have to build the POPL'25 or find the right simulation, and that's way easier than checking for all contexts.
So it's more on the negative side, where it could be of practical impact.
Yeah.
Okay. Yeah. Thank you.
Okay, could our next speaker come up? And I have a question for you as well. So in your syntax, in your reduction rules, you treat like a black lambda with a white application the same as a white lambda with a black application. Did you ever want to distinguish data going in and data going out?
I think that's an interesting question. That's something that people have asked me before, and we've not looked into this. I think this doesn't serve our purpose right now, but it might be interesting where we have like only communication going one way, or we only want the programs to be able to access them from the context, but not talk to it back. This would be interesting, but we've not looked at it practically.
Okay, thank you. So let's thank Adrian again. Okay, so our final talk of the session is going to be given by Jan van Brugge from Heriot-Watt, and he's going to tell us about rule induction for syntax.
Yeah, hello. I'm Jan, and this is joint work with James McKenna, Andrei Popescu, and Dimitri Traitel. And I present Baron-Drake convenes with Knaster and Tarski, strong rule induction for syntax with bindings. So what's the key problem here? So assume we have some relation defined over syntax that contains binders. In this case, beta reduction for lambda calculus. And we want to prove some property about the system. In this case, we want to prove, okay, if I can step from M to N, I want to also know that I can step from M where I do a substitution to N where I do the same substitution. Fairly simple property. Ideally, I want to prove this property by induction on the relation itself. I do not want to prove this by induction on one of the arguments. That will make the proof much harder. However, if I look at the Xi case, I will end up in my goal with a substitution over a lambda. So ideally, to progress this proof, I would need to move the lambda, the substitution into the lambda. However, I can only do so if I know that the variables are not the same. But our assumption doesn't give us this extra information. So at this point, I would be stuck in the proof, and I would need to do a lot of manual busy work to get this proof to work. So what we need here is the variable convention that says, well, the binders we introduce in that case are different from whatever I care about in it, or the free variables in this case. So how is the status quo here? So in pen and paper proofs, this is rather easy. We just say, yeah, well, we assume variables are bound are different from the free ones. Then it depends a bit on the representations in theorem provers. For de Bruijn, we do not need to strengthen anything. However, in the proofs, we then get shifting bureaucracy with the substitution. There are techniques to avoid that, but that's the main issue with naked de Bruijn. Higher order abstract syntax, if it works great. However, it's hard to model binders that are more complex than what the host language provides. And also for some proofs, having a deep embedding of a language is better. So in nominal, or in this case Isabel, to be precise, there is prior work on this in the form of nominal too. However, this has some annoying limitation as the authors themselves state. So what are these limitations? So if I have the beta rule, to be able to derive an induction theorem that has the variable convention built in, for nominal, we need to attach extra side conditions, extra freshness side conditions to these rules. And in this case, the side condition is not like anywhere presented in a textbook. It is not needed because substitution doesn't care if the result has the variable again. It's just there so we can derive this strong induction theorem. So that's not nice. This gets even worse in more complicated examples. This is from our paper. This is the process calculus, and everything that's colored gray is extra side conditions that should not be there. And that's the status quo for this. There's another problem. They employ like syntactic criteria on the rules that define our relation. And this is syntactic criteria, which mean it rules out very useful things like quantifiers and higher order relations. So our contributions in this work are, we provide a generic semantic criteria that is detached from the specific syntactic format of the whatever rules we define. And we have an implementation in Isabel Hall that takes an inductive predicate and a proof of this criteria and gives back a strengthened induction theorem, which can then be used to do proofs like mentioned in the beginning. And we even have a heuristic that is implemented, which can in many cases prove this criteria fully automatic. And to validate all of these, we have provided several case studies, which I will talk about later. So going one step back, how can we actually bring this rather textual definition of a relation into a theorem prover? And what we mean when we talk about these rules is like that beta reduction is the smallest relation that is closed under these introduction rules. And if we say, well, the rule is smallest and closed, this might scream a fixed point to you, to the avid reader. And that's exactly what we do. We represent inductive relations as fixed points of some operator. So how do we find this operator? Well, we want to fixed point which will be a relation. So the first argument will be the relation we define in the fixed point. And in this case, our relation has two arguments, the left and the right-hand side of our stepping relation. Focusing just on beta itself, in this case, we don't have any assumptions. We just need to constrain the left and right-hand side to have the right shape compared to what we wanted. We can do a similar thing for the psi case, just that we have now an inductive step. So we use that first argument that represents the relation itself to mean that. And of course, the other rules work exactly the same. So now we can define beta reduction in a theorem prover. And because this function in there is monotonic, we know, thanks to Knaster and Tarski, that this fixed point actually does exist. So this is nothing new. This is standard. It's already implemented in Isabelle for many years. So how can we bring binders into that mix? We need first to know in every case what are the variables that this case opens up. For this beta reduction, there's only two cases, this beta, which mentions a naked binder, and the psi case. So we record this in this extra argument like this. And it's pretty clear that this operator is still monotonic, so there is, again, a fixed point of this thing. And we can define this called beta g, which just adds an existential for this thing. So this is not yet an improvement over the normal beta reduction, but we will improve this later on. But for this simplified version, it's very trivial to prove that this forms the same relation as the original beta reduction. So before we can actually bring in the strong induction, we need to have some extra criteria on our relation. One, the arguments need to form nominal sets. So a nominal set are two sets, V and A, with a permutation operation, which maps from V, which will be variables, or everything you use to represent variables, to a bijection of that to a function on the set A, and a support operator which extracts a set of these variables from a value of the set A. In typical nominal logic, this set V is implicit the set of atoms that is axiomatized as part of the nominal logic axioms. We work in higher order logic without any extra axioms, so we leave this to be decided by the user. In particular, we can say, well, we use strings for our variable names, and our A is the set of, or the type of lambda terms. And then permutation becomes substitution, and the support are the free variables of the term. We also need two extra conditions, equivariance and reachability. The relation is exactly then equivariant if we permute with a bijection, in this case pi, all the arguments to the operator, the relation still holds. So this will capture us that we do not depend on the particular choice of names. This will rule out predicates that, for example, strip binders off and store them in a list, something like this, because they would not be equivariant. The other condition is refreshability, and this distills this what we mean by by freshness. So if we have our rules for every choice of rules, we need to be able to find a set of binders that is different from all of the free variables that appear in the rule. And that's exactly what captures the variable convention by meaning the bound variables are different from the free ones. Note that this is the generalization of what nominal 2 provides. So nominal requires you to have that be inherent. So the B that you use in the rules needs to already be fresh. And that's the main source why we need all of these extra side conditions, because we make sure that the free variables do not clash with any of the binders. So if we have these conditions for our relation, we can define a new thing called beta fresh, where we add these extra assumptions inside the fixed point. And with these conditions, we can prove that this is the same as the beta g we mentioned earlier, and as I said, the proof that beta g is the same as beta is trivial. So at that point, we can use the induction theorem that stems from this fixed point of beta fresh. We can use it to build to provide an induction theorem for beta that has the freshness built in. So how does it look for the user in Isabelle itself? So this is a normal Isabelle inductive definition, like many people probably have used already. And this is the new part. We can use the binder inductive command to strengthen this step relation. And in this case, as I said, we have implemented a heuristic. We do not need to prove either the nominal set structure nor the equivariance or refreshability. It's all automatic in this case. And then the proof I presented on the first slide is easy with this binder induction method we have implemented that lets you avoid the variables of certain parts in your rule. So what are the key advantages of this approach? So this is completely independent on how we state our rules. There's no syntactic limitation on what we can write and what we cannot write. They are all fixed points in the end. And we do not need to have these extra side conditions that are just there to satisfy the system. You get the freshness as an output of this process, not as an input. And this also, of course, has the bonus that you do not need to prove that the version with side conditions is the same as the version with outside conditions, because this proof, as seen earlier, we can do automatically. So in the paper, we have a bit more. We have generalizations for using inductive information for refreshability. That's also why there's two separate commands for this. So you can do normal inductive proofs in between and then use these proofs to strengthen. We have support for infinite types for this by generalizing what a nominal set is, and also non-equivariant relations. And we generalize this based on the case studies. So the first one is, of course, the beta reduction I talked about the whole time. Then transitivity of subtyping in system F sub. This is interesting because it exactly requires this inductive information. Reduction in the process calculus, which is interesting because of the scope extension axiom, which has a weird binding structure within the relation, in the reduction relation. And Damiano-Mazza's infinitary lambda calculus, which forces us to reason about infinite syntax and non-equivariant syntax. Of course, we stand on the shoulders of giants, so very important for this work are like ideas of nominal logic by Pitts and Gabay, and also work specifically in Isabelle from Urban, Karliczek, Berghofer, and Norrish. And more related was, of course, in the paper. So to summarize, inductive definition are least fixed points. Refreshable and equivariant relations we can strengthen to have nice induction theorems. We can automate most cases fully and many cases mostly. And this is general enough to work with infinite syntax. Thank you.
Okay, so we have plenty of time for questions. So is this on? You might be muted.
Okay. Hello? Okay, cool. Thanks for the talk. So you mentioned in the beginning kind of one reason you didn't want to look too much at higher order abstract syntax was that it doesn't generalize well beyond the kind of host notion of substitution. Do you have any maybe progress on like case studies or some inkling as to how this worked for a substructural type system or something like that?
Sorry, I didn't understand. What substitution?
You mentioned in the beginning that higher order abstract syntax wasn't a good approach for you because it was hard to generalize beyond the like host notion of variable and substitution. So in this setting, I guess I'm curious what that looks like. If you have any like case studies or at least like thoughts about extending to something like.
Yeah, so we don't we haven't looked directly at higher order abstraction because we work in Isabelle mostly, and we wanted to bring this to Isabelle. And Isabelle has a very limited, like it has only single binders.
Oh, sure. So I'm not saying you need to justify that choice. I'm just asking, like, does it?
So no, we hadn't
yeah,
looked at
okay.
anything from higher order abstract syntax because the context is just not
But
there.
I mean, like, do you have any? Sorry, do you have any thoughts about like a linear type system or something like that in this setting? Never mind. It's fine. I'll ask you offline. Yeah.
What system?
This.
Yeah,
system
this.
that, yeah.
So all the case studies are done with the automation and the system we developed. So because your linear type system would be a deep embedding anyways, it depends on what rules you define. So yeah, it would work with anything.
Okay, thank you.
Okay, do we have any other questions? There's some over there.
So very nice talk. Thank you very much. You were mentioning rules that were difficult. I'm using the open rule in the pi calculus, where you have a binder on the left-hand side, which disappears on the right-hand side. So it's bound on one side, but free on the other. So in nominal logic, that actually means that you must place an explicit permutation in your rule in order to make this work and keep it equivariant. Is this one of the rules that would still be a problem for you?
No, so actually for the pi calculus, the heuristic is strong enough to work with that. So we do not need, the user do not need to put any explicit permutation or anything on there. The whole permutation structure, the normal set structure is fully implicit.
Including the open rule?
Including for, yes, we have both late and early transition fully formalized in Isabelle, in one of the case studies.
Okay, any other questions? Be on this side of the room. Okay, I have one question too.
Yeah.
So you did this all in Isabelle. Have you thought what it would look like if you tried to do it in Lean or Coq?
So the main problem there is that we work with names. And representing names without quotients is annoying. So that's why we have not looked more. Probably if you use something like higher inductive types in Agda or something like that, this would be adaptable. But without quotients, I don't think this would be very usable for the use, because we do make use of equality for these alpha equivalent types.
Okay, we have one more question over there.
So I wanted to, so this is like, I was paying attention to some of these things where we were just dealing with a more fundamental problem of binding in the first place when I was a grad student a couple decades ago, and then I was away. And so this is sort of extending on the maybe a clarification of the standing of shoulders of giants. Where does this, can you say a little bit more about what this does, that the techniques that were developed in Coq don't do? Where a little bit more about the diff between what this enables and what, like, you know, the locally nameless and cofinite quantification. What the techniques that are used in other systems are.
So I'm not familiar with cofinite stuff, but for the Brown or locally nameless, it is the main difference is that you do not have to do any reasoning. This is more work to set up. Mm-hmm. But once you have a setup, you just have an induction theorem, and you don't the freshness and does not leak into your proofs. With different versions of the Brown, you will have some sort of shifting lemmas or in your actual proofs about the system, because the Brown is fundamentally leaky, and also locally nameless has the same problems. So that's the main. Like, this is more work to set up, but we can automate that. And afterwards, it gets completely out of the way, and you just use binary induction, and you just get extra assumptions for freshness.
Okay, so let's all thank the speaker one more time.
Hi, everyone. Hi, everyone. Welcome to the last session of POPL proper. So we have a session about proof assistance. And to start us with, we have a live talk by Rao about WebAssembly mechanization, and he's also in the job market. Take it away.
Thank you. Testing. All right, this works. So thank you, Druby, and good afternoon, everyone. My name is Rao, and I really thank you for staying until the end of the POPL to attend my talk, which is about a special design we named the progressful interpreters, and about its application in our WASM mechanization. So this is a joint work with Stefan Radzug, Current Walt, and Philip Gardner. So I'm actually going to start my talk by discussing a slightly different but still motivating method, talking about how to derive a sound interpreter from a constructive type soundness proof. And along the way, I also recap some of the important concepts in type theory, which are also key components in our WASM cert mechanization. And it is only in the second part that I'll go to our progressful interpreter and discuss about its advantages. All right, so let's get straight to the foundation. Let us suppose that we are started with a relatively simple type system, which can be described by a binary typing relation between the set of expressions and set of types tell. And on the other hand, we have a small step operational semantics between the set of expressions. So it should be well known that the type soundness property is defined usually as two parts, including the preservation property and the progress property, where the preservation property would state that if you have a well-typed expression and if the expression steps to a new expression in the operational semantics, then the new expression has the same type as the old expression. Whereas the progress property states that starting from a well-typed expression, you can either take a step in the operational semantics and, or you know that your input expression is actually a terminal expression of the language. So getting to the interpreters, the one-step interpreter can be thought of really as a function that takes an input expression E and produces one of the several possible results, and including one of which being a successful execution result that returns a new expression E prime. And in our setting, we define the soundness of the interpreter to be a proof of the corresponding reduction term when the interpreter returns a successful step. So up to now, all of this have been mechanized in our prior work of mechanization of WASM 1.0. So type system and operational semantics and proofs and etc. But this is not all of it, and we actually have more of the proofs and definitions and even more about talking about all different aspects of WASM. So this is quite troublesome because WASM is not something that is static. It is a kind of still actively evolving language. So whenever there is some kind of change in the underlying semantics, then that means we have to actually go to each of our different components and make sure that we are updating them in the right way, which is pretty inconvenient for us. So naturally, we are then thinking of a method of perhaps merging some of the components here into one. So it turns out that there is a particular resemblance between the progress property and a sound interpreter, in the sense that both of them take an expression E as an input, and in one of the cases, produce a new expression E prime and the corresponding proof term of the reduction relation. And this resemblance actually motivates the key idea of how to derive a sound interpreter from a constructive proof of progress and preservation. So to be more specific, let us suppose that we are started with a well-typed expression E of type tau. Given that the progress proof is constructive, which means that by Curry-Howard isomorphism, it can be think of as a computable progress function, we can apply it to the starting timing term and therefore obtain a new expression E prime as well as the corresponding proof term for the reduction. And the next important step is that we can actually apply the preservation property to the above two proof terms and construct a new proof term of the current expression E prime and its associated and the associating type tau. And in this fashion, our computation can basically continue indefinitely until, of course, if the progress proof decides to terminate us at some point. So I should really mention that this idea is not new. It's not invented by us, and this might have been folklore knowledge among experts in certain fields of type theory. But in our particular case, it came to us via a series of popularization by Phil Wadler a few years ago. So I have another side comment about the color scheme I'm using here, because on another day I was thinking about this, and I found that there's a clever, not clever, there's a tricky resemblance between this and a typical CMYK printer, because that's how the printer does its job. It doesn't carry the green ink, but it rather prints the green color by mixing the cyan and yellow. All right. So all of this sounds good so far, and we went on and implemented this method on top of our mechanization. So the short story is that it works to some extent and with additional efforts. But we found out that there are actually quite a lot of limitations to this method. The first one really is that if you are really counting on the type soundness proof to do the execution for you, then you are having the issue when you are trying to extract the proof, or the interpreter, from the proof assistance to a language like OCaml, because these proof terms can now not be erased during execution. So this is quite unfortunate for the interpreter, because it means that you are carrying a much larger runtime representation, which slows it down by quite a bit. So in fact, in our experiment, we found out that there is actually a complexity level inefficiency, which is displayed by the benchmark here. The benchmark basically is on a very simple WASM program evaluating the values of the Fibonacci numbers by a very simple linear loops. So supposedly it should have a linear complexity. But what we found is that the type soundness interpreter actually demonstrates exactly a quadratic behavior, which is quite interesting on its own. So we went on and investigated what the source of this problem is. And it turns out that there's a explosion of growth in the sizes of the proof terms. And it is due to a specific interaction between some of WASM's typing rules and our existing type soundness proof. So naturally, we then went on to try to see if we can actually solve this problem. The answer is yes, but it is also very difficult to do that, because in this structure, when you are trying to optimize the interpreter, you are necessarily dealing with the proofs. And the second point, which is more important, is that the changes required are actually really awkward, and in some cases just plain stupid, if you view it from a perspective of doing the proof. But anyway, in the end, we found out that the type soundness interpreter can be optimized to linear complexity, although it is somewhere around 70 times slower than the original one. The key takeaway here is that even a subtle difference in the proof structure can have a great impact on the speed of the interpreter, which is something that you certainly don't want to care about when you are writing the type soundness proof, which is already quite tedious. And the last limitation, which is slightly non-obvious, is that this method actually requires a separate function to get you started, because in real world, you don't actually have programs with the complete proof terms of the typing judgment for you. And you have to construct that by doing a type checker or something like that by yourself. And we know that this is generally a difficult problem for programming languages and can be undecidable for certain languages. And we know that a mere type annotation is insufficient for our purpose, because the type soundness proof actually requires the concrete typing terms instead of just a type annotation to run. But fortunately for our case, this can be done for WASM because of the existence of a validation algorithm, which, although in the end it did require additional work by doing some more correctness proofs on our side. So these limitations really mean that we shouldn't be doing this method for the long term. And in the end, so after that, we are trying to see if we can view the problem from the other direction, which means that instead of trying to generate programs from proofs, can we write programs that carry the proofs? And this is where the progressive interpreters come in. So let us start by revisiting the traditional structure of a one-step interpreter, which is as described previously. It is a very well-known method in several books and many places, that you can attach a certification of correctness to certain branches of execution, so that you are getting a dependent typed functions and which certify its own correctness. So what is the most important part of our progressful interpreter is that being motivated by this method, we similarly augment the other cases of execution by a similar certification. So for the case where the interpreter terminates, we require a proof that the input is actually terminal. And the key point here is that for the case where the interpreter wants to crash, we actually require a proof that the input expression is malformed. And to be more concrete, we define it as it cannot be associated to any type of language. So what good does this particular crash certification does? It turns out that if you do it via a contrapositive argument, then this specific structure induces a progress proof for free. Because suppose if you now started with a well-typed program, then by applying the progressful interpreter to the program, you would know that you can never land into the crash case. And as a result, you're either getting a successful reduction or a terminal result, which is precisely what the progress property states. Another thing to mention, to note here is that this progressful interpreter provides a guarantee that is stronger than the original soundness, because now any valid input has to actually make a progress. All right, so this is about the abstract structure. Let's look at how it is actually done in like the WASM search mechanization. So I'm showing a kind of like simplified structure of the one-step interpreter here, which is like, to be honest, like quite similar to the abstract version I've shown earlier. So we have a fixed point of a one-step interpreter taking the different components which form the WASM configuration, and it returns one of the several results, which includes the previous three, but plus a bit more to deal with WASM's control flow, which we'll omit here. The progressful interpreter, as promised, augments the type of the return type to a dependent type, and as a result, attach a certification to each of the case of the execution results. All right, so we have successfully implemented the progressful interpreter on top of our WASM, like our old WASM 1.0's work. And the next question is, can we actually do more work on top of that? Because recall that our original purpose was to maintain the mechanization. So the first thing we tried is to implement an optimized runtime representation, and this is an idea from the Isabelle counterpart of the mechanization, which targets at evaluation contexts. The result is that we get an interpreter which is vastly faster on programs with heavy control flow or function calls. And incidentally, it actually produces a smaller code base because the way that the control flow are dealt with is simplified. And the second significant part of our work is that we have updated the underlying semantics to the much larger WASM 2.0 feature sets. And of course, now this is in our subjective experience, but we found out that the process of updating the interpreter was fairly easy. And in the process, we have also found and fixed several errors in the official specification. All right, so it's time to display some benchmarks for the optimization. So this is a slightly different benchmark that similarly computes the Fibonacci values, but it is done in a way that via function calls, recursive function calls. So which means that no intermediate values are remembered, which means that this program will involve quite a lot of like function calls and returns. So as expected, the type soundness interpreters, being like optimized or not, are the slowest ones, which are actually even like around 3 orders of magnitude slower than the WASM's reference interpreter. And next in line are our progressful interpreter and the Isabelle counterpart from Watt. And they actually have similar performance for our optimization target. And for the sake of completeness, we have also like tested the industrial runtime, which is named WASM time by Bicycle Alliance. And it is around 2 orders of magnitude faster than either of the optimized interpreter from proof assistance. But we hope that this is kind of expected. All right, so reaching the end of my talk, I want to quickly describe 2 related approaches to our work. So the first one is the use of an intrinsic typed representation, which means that the programs themselves carry their types with them. And we know that the distinction between the type soundness interpreter and our progressive interpreter is pretty big in our setting, because WASM has a extrinsically typed semantics. And in the other case of intrinsic type semantics, then a proof of progress would actually be quite similar to an interpreter itself. And but do not forget that there's a similar issue of how to get this initial timing term, even if you are using the intrinsic type representation. And the second related approach is the use of definitional interpreters, which means the use of an interpreter as the normative definition of operational semantics, which certainly helps to cut away this, even the operational semantics from the mechanization. But this really doesn't help our purpose, because in the end, our mechanization is supposed to reflect WASM's official semantics. So if we cut away the only connection, then we are losing the trust of our mechanization here. And another point is that this method also only works conveniently for a completely deterministic semantics, which WASM is unfortunately not. All right, so to conclude my talk, I'll give a summary of what we have done in this work. We have, to our knowledge, for the first time, we have implemented an end-to-end progress and preservation interpreter for a real-world language WASM. And we have also investigated the source of its efficiency and tried to perform some optimization on that, which doesn't work. And the second is that we have proposed this method of progressive interpreters and implemented for WASM Cert 1.0. And on top of that, we have performed some optimizations and updated the semantics to WASM 2.0 and correcting some errors on the way. So this concludes my talk, and thank you again. I'm happy to take questions now.
Well, we thank the speaker and open the floor for questions.
Thanks for the nice talk. Yeah, so this idea of delaying the type checking to runtime, that's very nice. So if I'm in a situation where I did do the check already in a different stage, is it possible to, you see a way to basically optimize your interpreter to remove those branches?
I don't think this is really possible because, well, if you are sticking with the type soundness approach, then there's no way you can really like escape from having to use the typing term, because like essentially like the process of that execution is like interleaving progress and preservation, and you are producing a new kind of like proof term at each step. So having a initial one doesn't like help coming up with the doesn't help you immediately get to the next ones.
Any other questions?
I have not understood what is your initial definition of the semantics of this WebAssembly. You have a little row here. How is it defined?
Sorry,
from
which
E
one?
to E prime. That looks like a transition semantics.
Ah, yes. So
and how is it defined?
Yes. So in the formal semantics of WASM on their website, this is defined as like basically a small steps relation. And in our work, in our mechanization, this is captured by like basically a line by line corresponding inductively defined relation in ROC.
And you cannot extract an efficient interpreter out of these semantics?
Well, an inductive relation itself is not executable, right? So the other way is certainly possible. And like as I said, like another issue with WASM is that the semantics is not really deterministic. So so you have to choose a branch to go like when there's a divergence.
Okay.
Let's thank the speaker once again. Oh, the mic. Next, we have Jeremy to talk to us about compositional verification. Thank you. Yeah, you can.
Can you hear me all right? Cool. So yeah, I'm Jeremy. I work at Yale University in Zhong Xiao's team, and I'm going to talk about work we did with Yu Zhang and Yuting Wang. And the goal of our work is to figure out how to verify heterogeneous systems. So just to give you an example of the kind of thing I'm talking about. So here's a fairly simple program built out of 2 modules, right? One is written in assembly. It has some kind of hello world message in here. Then at some point, it's going to call into this C library file that applies a ROT13 transformation to the message. Then it's going to invoke the right system call to display the message on the standard output. Now, we could have a second program that also uses this ROT13 library, right? Whose goal is to decode this message. And so it's going to read some data from the standard input, apply this transformation, invoke the right system call to display the result. And so what we want to verify here is that if we compile and link these 2 programs in the obvious way, and we combine them together like that by feeding the output of the first to be used as the input for the second, then it will indeed display the message hello world on the standard output, right? And this is not a complicated problem in and of itself, but what's complicated here is that, so of course we have semantics for assembly languages, the C languages, we have all kinds of program logics that can help us do that. But here we're interested on how these programs are going to behave within an environment, right? And we're going to have multiple languages that are going to interact with one another, things like that. So if we wanted to verify this the traditional way, we would have to model all of these details of like how Unix processes communicate through a pipe and so on and so forth by building a new operational semantics that has everything in it. And by figuring out ways to reason about it, right? So what we would like to do instead is to have a more compositional, more convenient way to build a model of this system from existing components, right? Certified compilers, program logics, things like that. And to be able to reuse these reasoning techniques from the pieces we use to build our model of the system. So our proposal is to use semantic level refinement frameworks to do this kind of thing. Of course, what that means is that we'd be able to express a high-level specification for the behavior we want, right? So we want that command to display hello world. We'd be able to define our model in a more flexible and compositional way by reusing existing things. Here I've described, okay, if you take all of these assembly files, link them together, load them as a command, and combine the resulting processes with a pipe, right? That's the thing we want to verify. And we want to be able to do that through a refinement paradigm where we can step by step go to a more concrete version of our specification until we reach the concretely implemented system, right? So the problem is, in a heterogeneous context, things don't always work as smoothly as that, right? Because if you think about it, you're going to have C program, assembly programs involved in this thing, higher level views of Unix processes, and so on and so forth. So things get a little bit complicated. But what we did is we used FX signatures to provide a type for our components. And we'll have components that use the operations in a signature E to implement the operations in a signature F. And the key ingredient of our framework is that we generalize these refinement steps to refinement squares. And the additional ingredient in refinement squares is that in addition to relating things of the same type, we're going to be able, when we have things of different types, like in this case, a C and assembly module, we're going to be able to express the abstraction relationship that makes them correspond to one another, right? So in this case, this refinement square corresponds to the compiler correctness property from CompCert, and we can express as this so-called refinement convention, the calling convention that's used by the compiler to validate this refinement. And using this kind of refinement squares, will be able to construct complex two-dimensional refinement proofs like this, where you'll be able to reuse properties expressed as refinements, things that you've proved yourself, like this code proof, or things like a compiler correctness theorem, a linking theorem for the assembly language, and other things that I'm going to discuss. So that's the basic idea. We build a framework where we have this notion of not only horizontal composition between the components of a program, but also vertical composition of abstraction relationships and of refinement squares. I'll talk a little bit, if I have time, about spatial composition, which is how we deal with how state is used in the different parts of the system. And we were able to mechanize this framework and incorporate ComCert-O, which is our version of a compositional version of ComCert, to be able to reuse all of these things that are associated with it. So I'm going to describe how this two-dimensional refinement framework works a little bit. Then I'll get into how we deal with state and go over a conclusion. So, sorry, let me. All right, so as I said, we are using a notion of FX signature to type our components, right? So an FX signature is just a set of operations, and for each one, a set of possible outcomes. And our strategies have these types, and what that means is that their behavior is going to be like this. Somebody is going to invoke an operation of F, and that's going to activate our strategy, which can then make a series of calls into E, and finally return an outcome for the operation that was invoked in F, right? And to give you an example, the interface of commands is very simple. They have one operation, which is run the command, and the outcome will be an exit status for the process, right? While the command executes, it can use read and write system calls, which means that in the end, we can use strategies of this type to specify what a command does or what a Unix-like process does. So as an example, our decode process, right? We can give this kind of specification for it, which says that if you run decode, it's going to read some data from the standard input. If it reads that specific message, it should write this message to the standard output. Now, given two strategies that interact over a common FX signature in the middle, of course, we can compose them in a typical sort of game semantics kind of way, right? So we can let them interact over the signature F and hide that signature to obtain a strategy that goes from E to G. And to give you an example, we can use this type of composition to describe what happens when, let's say, decode.c makes calls into row13.c, right? So we can combine the semantics of these two C components to see what happens when we run them together. Another way we can compose things is side by side. So here we don't let them interact, but we just put two strategies side by side and let them implement the sum of their operations, right? So the type of the resulting strategy will look like this. One example is if we want to sequence commands to implement this shell semicolon operator, right? The first thing we want to do is to combine them side by side like this. So we get a strategy which has two run operations that allows us to run either command as we wish. And then we can combine this with a sort of scheduler component that first runs the first command, then the second command, and returns the exit status of the second one, right? So that's how we can model the kind of shell operators like the semicolon or the pipe. So we can use this very simple, elementary horizontal composition principle to build more complicated things. All right, so things now are getting interesting because we're going to talk about our refinement squares. So the magic ingredient here is this notion of refinement convention. And this refinement convention is going to tell you how the operations of E1 and E2 correspond to one another, but in a way that can embed some state and be history sensitive, right? So once you've done that, you can then specify that two strategies will have the same behavior in terms of the shape of the behaviors, but the specific operations will be translated between high-level views and low-level version, right? And all right. So if we use trivial refinement conventions, we'll recover a normal notion of refinement where E1 and E2 are the same, of course. Now, these refinement squares can compose vertically, right? So what before would be transitive refinement, where we can just combine things in this way. Now, when the refinement conventions are involved, we need to compose the refinement conventions themselves to compute what's going to be the abstraction relationship in the resulting composite refinement, right? What would be the monotonicity of, let's say, this layered composition operator in a classical framework? Now it's going to become a horizontal composition of refinement squares. And when refinement conventions are involved, you want to make sure that the two refinement squares agree on the ways in which the operations of f are realized as operations of f prime, right? So, and we have similar rules for flat composition that I'm not going to get into. So that's one of the basic two-dimensional framework. The idea is that a lot of properties, different properties, can be expressed as refinement squares, and then we can mix and match to build complex refinement proofs. And now I'm going to talk a little bit about how, in particular, that comes in when we're going to talk about state. So to deal with state, we use this spatial composition operation. And spatial composition is going to act on all of the objects in our framework, right? So for fx signatures, what I'm doing here is I'm annotating every operation and every outcome that's found in the signature E. I'm going to annotate it with a current state snapshot of type U, right? So that means in the case of, maybe you saw before, for example, I had this C at mem signature, and that means we have C calls annotated with the current state of the global C memory, right? Now, strategies, if we have a strategy that goes from E to F, and we extend these signatures with some state, we can let the strategy do its thing and just pass along the state component that we've added. And optionally, we can also add a transformation to the state that acts sort of in parallel with the strategy L, right? Similarly, we can define same kind of thing for refinement conventions and also compose refinement squares, right? So you can imagine there's a third dimension, and you can sort of flatten the two squares together. One that's about the strategy, one that's about the state transformation. Now, what are we going to do with that? So let me switch gears and think about what will it take to implement a counter. So here I have a very, very simple specification for a counter where you call inc once, it's going to return 0. The next time it's going to return 1, and so on and so forth, right? And we want to implement that with a C library that uses this variable. I mean, you understand this code. I don't need to go over it. So what you can remark here is that a specification uses an implicit notion of state, right? Whereas, of course, our C semantics are going to tell you how like the variable C is going to be modified by this code and so on and so forth. It's going to use an explicit state that's going to be concrete in terms of C value and live in a global memory state. So how are we going to bridge these two views is the question, right? So the first step is we can sort of deal with encapsulation by using this state transformation primitive, which is going to hide state component of type U by using an initial state U0. And what that means is that this counter, right, we can give a specification that uses an explicit state, natural number as explicit state, and that's just going to say, okay, if we're invoked in the state n, we're going to return n, and the new state is going to be n plus 1. And we're able to sort of encapsulate this state to recover our encapsulated specification. Likewise, if we have a relation between this abstract natural number and the concrete memory states, we're going to be able to use this kind of refinement square to show a refinement between the abstract and concrete state. And then we also have a way to deal with how this value is going to sit within the global memory, right? We adapted the notion of separation algebra to be used in the context of our refinement squares. And we were even able to formulate a frame property for the C-Lite language in the form of one of our refinement squares. So by combining all these kind of ingredients, we were able to incorporate Concerto in a framework. We defined a new language, C-Lite-P, that has like private encapsulated variables. We were able to redefine a whole theory of certified abstraction layers using these basic ingredients. And of course, Modal are example from the introduction. We hope to use this kind of frameworks as coarse-grained glue for reusable certified components, right? And together, I think we'll need to incorporate more program logics and things like that. Adding concurrency is also a very important goal. And it will be useful to make more explicit connections with higher category theory, which is a theory of what happens when you have these different composition operations that interact with one another and allows us to think geometrically about this kind of thing, right? So thank you for listening. I'll be happy to take questions. I want to point out, if you read our paper, that we were mistaken in our characterization of CCR, which does support some kinds of encapsulation and certified compilation. So we're going to publish an updated version of our technical report with a more detailed comparison with our own framework. Thank you. Yeah.
We thank the speaker, and we have time for a question.
Hi, Max New, University of Michigan. So I have a question about category theory, which is, so I guess this is a double category, right? This
Almost.
refinements, almost?
Yeah, there's some technical details, but in spirit.
Okay, because what I was going to ask is one of the most important new things you can define in a double category is when a vertical morphism can be sort of like minimally or maximally turned into a horizontal morphism.
Right. So conjoints and companions,
yes,
right?
Exactly.
So those are horizontal morphisms that can correspond to vertical morphisms in a way. So let me go back to this diagram here. Here, there are some versions of conjoints and companions that are involved in these corner squares here, right? So, for example, when we model how you take an assembly program and turn it into a command, this entry morphism here is going to tell you how the run operation is going to trigger a call to main, right? That's like the bootstrapping code that the thing uses. But then when we look at, when we want to prove that our code is correct, we have to take into account this sort of correspondence. So that's a kind of situation where you have refinement squares that you have strategies that have conjoints and companions, and you can use them to do this kind of thing. Yeah.
Well, that's all the time we have. Let's thank the speaker once again. For the next talk, we have a recorded remote talk from Jocelyn. Yeah. And for questions, we have one of the authors here in person.
Hello, everyone. Thanks for having me. My name is Jocelyn Poiret. I'm a PhD student at Galinet in Nantes, working mostly on ROC and proof assistance. And today I'm going to talk about our recent paper on sort polymorphism, which is a newish feature that we're still trying to improve step by step. So first, I'm going to maybe introduce the problem that sort polymorphism is trying to solve. And then we're going to focus on the chosen solution, which is prenex quantification in our case. Then maybe we'll talk a bit about our efforts to write a new sort polymorphic prelude that makes use of those new features. And then maybe talk a bit more about the theoretical work that we did on this sort polymorphic system before concluding. So maybe to refresh your memories a bit about proof assistance, I'm going to talk about mostly ROC, but also a bit of Lean and Agda. So those proof assistants let us formalize mathematical reasoning using something called the propositions as types paradigm. So that means that we consider types to be propositions. And here, for example, you can see that I've written the basic tautology, which is that A implies A for any proposition A. And notice here that I'm quantifying over A in type. But quickly, users realized that we might benefit from having a finer notion of type because some types are better than others in some cases. So, for example, propositions, we should be able to erase them in extracted code because we don't want to manipulate complicated termination proofs, for example, when we just want to compute in the end. So that led to the addition of prop, and so types in prop are erased in extracted code. And also we might want to have something called strict propositions, which in ROC is represented by sprop this time, or just prop in Lean and Agda. So strict propositions, they're propositions whose proofs are all equal. So that means that we don't have to worry anymore about having proven some proposition in two different ways. The system is just going to regard them as equal. But of course, with power comes great responsibility, and eliminating from prop and sprop to type is more restricted than usual. So for example, if you want to eliminate an inductive from prop, you need to have it follow singleton elimination. And if you want to eliminate an inductive in sprop, well, it has to be the empty type. You cannot eliminate anything else. And so now you can see that we have three different universes, type, prop, and sprop. And you might want to have an identity function for them. But for now, what I can do is only write a duplicate definition for prop and for sprop. And that quickly gets a bit unwieldy and requires a lot of boilerplates. So maybe a more involved example is that of binary products. So in ROC, as of now, in the prelude, there is a distinction between and prop, which are just the binary products for propositions and for types. So as you can see, they're exactly the same definitions, where we just substitute prop for type. So that leads to a lot of duplication, lots of lemmas need to be proven for both of these, and they're just the same. So this is really unwieldy, and it's kind of unreasonable to keep adding new sorts if we're not going to make them more usable and more user-friendly. So Lean actually does have some solution to this, but it's only a partial solution. Prop and type in Lean are just synonyms for a single universe hierarchy. So prop is just sort 0 and type U is just sort U plus 1. So for example, in this way you can quantify over A in sort U to define the identity function, and this would work with both prop and type. So as you can see here, I can apply the identity function to true and nat. But this technique doesn't really work if I want to introduce the binary products, for example, because of those elimination restrictions I talked about earlier. And Lean really relies on eliminators to do its work. And so here it just throws out an error because it can't just derive a most generic eliminator. And also that solution doesn't really scale with newer sorts. Here it works because prop is impredicative in Lean, so you can just add it at the beginning of the universe hierarchy, but this wouldn't work with another predicative hierarchy, for example. So instead, what we chose to do was use something that was already present in Rock for some other reason, which is pre-next quantification for definitions. So this already exists for universe polymorphism in Coq. So for example, you can quantify over a universe level in the definition. So here I'm defining again the identity function ID, but it binds a universe level U that it's going to reuse to quantify over all types A of level U. And we're going to reuse the same system by introducing pre-next quantification by a sort variable this time, so S here. And we're going to bind S and U and quantify over all types of sort S and level U, and still give the same definition of ID. So here S stands for one of the three ground sorts, which are prop, type, and S-prop. And as you can see here, I can instantiate ID to make it work with true, which is in prop, and with nat, which is in type. And of course, the elaborator just lets us write ID of true. It can infer the proper sort here. And for the case of binary products, we can generalize them very heavily. So here I'm binding S, S prime, and S second. And as you can see, I can take a type of sort S, another type of sort S prime, and make a binary product at sort S second. So this generalizes and prod, but also a product of two types in S-prop that lands in type, for example, or just two types in S-prop that stays in S-prop. So this is very general. But of course, we have to follow the elimination restrictions I mentioned earlier. So suppose for now that we define sort polymorphic booleans. So they're booleans that live at a sort S. So I can instantiate them at type and I get the usual booleans, but I can also make them live at prop or S-prop. Then what I can do is I can always eliminate from a variable sort S to itself. So for example, here I can eliminate the booleans at S to the booleans at S and define the negation. I just match on the boolean and return the opposite boolean. But I cannot eliminate from a variable sort S to another completely unrelated sort. So for example, a ground sort like type. So here, suppose I'm trying to define a function that takes a boolean at sort S and gives me the exact same boolean at type. Well, I could try to do it by matching on the boolean and then returning the exact same constructor, but Coq is going to complain because I'm not allowed to eliminate from S into type. Because of course, if this definition was valid, instantiating it at prop or S-prop would give me something that is actually incompatible with the elimination requirements of prop and S-prop. And there is a very significant example of this, which is that of universes. Because universes, they all live at the sort type. So for example, prop is in type, S-prop is also in type, and type itself is in type, but at a higher universe level, of course. But that means that we can't eliminate something which lives at a sort S to its own universe. And you might know that because of its name, large elimination. And you might also know that it's the main ingredient to show that true is different from false. So that means that we can't show that true is different from false at a variable sort S. But it does actually work in our favor because true is actually equal to false in S-prop because strict propositions, all the terms of a strict proposition are equal. So this is actually fine and expected. So now all these features, they've been in Coq for quite a while now, but we haven't really seen a lot of adoption of those features. And one of the main culprits is that the prelude and the standard tactics, they both don't really support sort polymorphism. So for example, the prelude doesn't have the generic prod, for example. It only has and prod. And the standard tactics, they usually choke on anything that uses sort polymorphism. It's a bit of a chicken and egg problem. So we thought we could remedy this by writing a new prelude that uses universe and sort polymorphism. That way we'd also fix the tactics as we go. So that's exactly what we did for the paper. We have, for example, sort polymorphic lists. So it just takes a type at sort S and gives you a new type at sort S. And with that new prelude, we thought we'd try to target some higher level stuff. So one of our initial targets that we highlight in the paper is that of the setoid rewrite tactic, because it contains some Galena code and also some ML code. So the setoid rewrite tactic, if you don't know, is kind of like rewrite. It lets you replace terms in goals using some user-provided relations, not just the equality relation. But those relations, they might be in prop or they might be in type. And we might want to rewrite both of these, using both of these. So that meant that for setoid rewrites, the Galena definitions were completely duplicated for prop and type valid relations, which was kind of a nightmare to maintain. And with the introduction of sprop, no one bothered to actually add them to the setoid rewrite tactic. So there's nothing for sprop. So what we did is port all of this to a single copy that uses the sort polymorphic prelude, and that way we also support sprop for free. So this was actually a nice success that we got pretty early on. And maybe now we could turn to the more theoretical side. So our system that we call sort poly that we introduced in the paper, we tried to make it compatible with Agda and Lean as well as Rock, because you might want to be able to benefit from this in other proof assistants as well. What we did in the paper is study a couple of meta-theoretical properties. The main guiding principle that was used to inform our design of the system was that we should be able to monomorphize sort polymorphic terms back into terms with no sort polymorphism. So it does seem quite simple. Let me give you an example. For example, here the empty type that is sort polymorphic, so it leaves that the generic sort S. We can turn it into the empty types at prop type and sprop by just instantiating S with all possible values. So that's basically monomorphization. But this seemingly simple principle does give us a lot of power. For example, we know that sort poly is equiconsistent with the monomorphic system because we can just monomorphize back proofs of empty and we'd get a proof of empty in the monomorphic system. So this is really nice. And then later on in the paper, there's also a definition of a parametricity translation for sort quantification, which roughly means that if you have a sort polymorphic function, then what it does at different sorts is actually the same thing. So this is basically parametricity, but for a new kind of quantification. So in conclusion, what we hope with this paper is that we'll be able to, in the end, integrate the new sort polymorphic prelude so that users can enjoy better usability. Learning with Rock should probably be easier, but also that experienced library writers would be able to write less boilerplate. But also from the more theoretical side, we're hoping that implementers will be able to add new sorts to their language using our system sort poly as a backbone. That way they'll be able to focus only on the interesting features of the new sorts they're trying to add. And as an example, we outline a couple of them in the paper, but we have exceptional type theory but also type theory with ghosts, which is basically a refinement of the erasure property of prop in Rock. So thank you for your attention. Thank you for having me. And I think Nikolai is in the audience to take your questions. Thank you again.
Your microphone? Okay.
Yeah, I think it's gone. It's okay. Yeah.
We can take questions. We have some time.
Does the sort polymorphism affect like performance, like type inference or anything like that? Like if the whole standard library is now using
So
this?
for elaboration, for example, it improves the elaboration because in previous system, when you elaborate and you just define A and you don't say whether it's type or prop, the system tries to guess for you, and at some point it has to make decision. Sometimes a bit too early, and it ends up in error in type checking. Whereas now you can keep a variable and say I will wait as much as I can to elaborate and type check my term. So now we have an expression in Rock that does type check now, even with just using prop and type that we are not type checking before. So elaboration is improved. And with respect to performance, because there is already universe level attached to the universe, adding a new part, a couple instead of just one record, doesn't change much.
Any other questions? Yes.
Okay, so this theoretical framework of sorts, can that be instantiated with an arbitrary sort theory, and sort of what's the data of a sort theory then?
So you can postulate new sorts as axioms, and then you can add axioms that sometimes exist in these new sorts and so on. So you could define some part of modal type theory this way. Simple one, the one where the substitution is valid in the theory. And then because we have added also rewrite rules in Rock, you can also postulate computation in your new sort if you want to kind of maybe prototype a bit. We don't pretend that it will be a definitive answer to the extension of the proof assistant, but at least for prototyping, it's very easy because you just open a section, postulate a new sort and new rewrite rule on it, and you kind of have a new proof assistant.
You also need to specify which sorts can be eliminated into other sorts, don't you?
Sorry?
You need to specify how you can eliminate from one sort to another
So
sort.
for elimination, we need to do a bit some work because we realized by doing the new prelude that being able to abstractly postulate the elimination from one sort to another will be very useful as well. So in the graph, for the moment, we already have a graph of dependency of constraint between universe level, and we want to add a graph of constraint of elimination between sorts that will be used to be even more generic, and this way we could postulate elimination. But it has not been implemented. It's for future work, hopefully soon.
Okay, there's someone else with a question. Yeah.
Hey, sorry if this is a silly question, but why would a term not be monomorphizable?
Sorry?
Why would a term not be monomorphizable? You said in the presentation,
yeah,
you said, oh, we require that we can always monomorphize.
You mean how this theorem is not completely trivial? That's the question?
I thought that was a constraint you had.
Yeah, it's a constraint of somehow the elaboration of the system and all the elimination rules that we impose at the level of abstract sort have been done in a way that the monomorphization theorem works. So somehow it's kind of intertwined. But it's the sanity check of the definition of the system is that this theorem holds somehow. Yeah.
We have time for one more question if there is someone with a burning question. Yes, okay.
Did you find that you were able to incrementally migrate towards the more polymorphic prelude, or did you find you had to do it all at once or it would fall apart?
So we are trying to do it incrementally. So we already split the standard library with the core library in Rock. It's a kind of recent change, so that the standard library is still kind of oblivious from sort poly, and the core library is now fully sort poly. And then we have definitions to instantiate on ground sorts, and the standard library will be a bit less sort polymorphic for the moment because we don't want to destroy everything at once. At least we try.
Let's thank the speaker and Nicola once again. That concludes the session and also POPL proper. Thank you for coming.